Good morning. Welcome. My topic today is opening to promote the value of RISC-V and the Taiwan industry. So I have a few slides to share with you. First, welcome to 2025 RISC-V Taipei Day. We have been experiencing several years of RISC-V Taipei Day events. And this year, we make it even bigger. So thank you for attending. No matter your audience, your sponsors, exhibitors, and partners. So we respect whoever sponsored this event, and we know you aggressively put your resource and effort in this RISC-V ecosystem development. So we welcome you and hope you reach further success. Also, together with today's full-day conference, we have a 4-day pavilion in the main exhibit hall. So take time to visit the booth. Taiwan is in the center of the technology, design, and manufacturing. This is the fact. We hope everyone, no matter you are located in Taiwan or overseas, you have an opportunity to leverage Taiwan's value. We believe Taiwan is in the center of the semiconductor, chip, IT, ICT, ODM, OEM, system design, and manufacturing. Companies from TSMC, MediaTek, to ASUS and Foxconn, there are so many opportunities of business. No matter you come to look for market, customers, or vendors, partners. So with IC design, manufacturing, and application, I think they are the way to realize your value in Taiwan, and you leverage Taiwan and put, no matter it's your product or your software, whatever your effort, your result, then you can export to the world. One example, NVIDIA. They know how to leverage Taiwan's value, and they do it well. So they leverage the ecosystem of industry in Taiwan to make their AI industry ecosystem very successful. Now, let me also cover the subject of RBI successfully raising RISC-V open standard. RBI stands for RISC-V International Association. RISC-V enables the best processors. Okay, I'll have more details to tell you. It comes with the innovation. It is also an open standard that everybody can leverage. So the fact is that the leading companies in the world in different industries, including AI, including automotive for EV, and software or social media, they all leverage RISC-V today. So RISC-V is already one of the 3 world leading standards for ISA. Together with x86 and ARM. And RISC-V extremely fit the application for AI, and that is the subject of today's conference. So we know, like NVIDIA, they started to develop their a GPU with CUDA, put that in AI application, starting from 2006, not even 2007. I was wrong, because yesterday, Jason Huang said it was 2006. So it takes time, but later on you will know RISC-V is also fitting AI if you have enough time, enough opportunity to develop your product and fit to AI. So let's keep looking, because today there are speakers focusing their subject in AI. One example, again, it is NVIDIA. NVIDIA leveraged RISC-V to be their processor cores internally developed and applied. Here's are some examples. They have more than 30 different functional applications cases applied, and that they have a rich set of developed cores. They already reached 1 billion shipping in their NVIDIA chips in 2024. So we also see the active members working together with us in RBI from media. And this is their application example. NVIDIA's deep learning accelerator, they applied RISC-V vector engines and microcontrollers for their overall NVIDIA AI product lines. One example for RISC-V's success is that you can do innovation. You can raise a proposal to RBI's working groups in the technical steering committee. And you can also, by yourself, adding custom instructions to the design for your processor. Here's the remark. RBI's ISA module is not allowed to add or change, but you can follow the interface defined by RBI to design or add custom instructions. Now, let's take a look. The effort has been paid for RISC-V development. It's been 15 years, because last week it is the birthday for RISC-V. Okay, they celebrate 15 years anniversary in RISC-V Summit Europe. So that was May 2010. From UC Berkeley, after the birth and the first few years development, starting 2015, it became a open standard to the world. It opens to the world. Now, in 2020, the original RISC-V Foundation changed to be RISC-V International and moved to Switzerland. So from 2015, it became the standard, and during these years, it put much effort to develop ISA modules, to develop architectural specifications, and define the interface for custom instruction set. It defines the profile and even further platform, and to develop the ecosystem for RISC-V. Now, the working culture in RISC-V community is very, very good, very friendly, and it welcome everybody to join it. And further effort will be keep it to be an open standard for the world. So one example for RISC-V is really a better solution is that it comes with friendly interface that you can add your custom instruction. We call it domain-specific extensions, fitting no matter what kind of application you have or you are doing. Along these years, we know RBI rectified instructions. Here, there are 2 pages that I listed the instructions rectified from 2021 till last month. And some of them are really important and significant, so I mark them as red color. For example, in 2023, there are RISC-V profiles, RBA 20, RBA 22, and then in 2024, RBA 23 was defined and rectified. So what is the RBA 23? It is a profile that rectified in 2024, and it is the major effort to make RISC-V can be applied as a general application processor. So, for example, we know RISC-V can run RTOS, RISC-V can run Linux, but now RISC-V is able to run Android system. So, this is the evolution. Gradually, you will see more and more vendors that they put their effort in the IP, then the chip, then the system, that to the end user with a RISC-V application processor that can run on over Android system and to become handheld gadget or some home appliance that you can see in near future. So the RBI trend, I would like to say, the beachhead for RISC-V is like ARM, like other proprietary processors that they entered the market, like a finite state machine, deep embedded controller at the first, and then they became to deal with digital signal processing, vector processing, and so on. And gradually, a matrix instruction will be added. Okay, and the third step is to enter, which is so-called ecosystem dominant market. For example, microcontrollers. And application processor is the fourth step for RISC-V to enter. So again, the general purpose application processing era for RISC-V is coming. The ecosystem with RISC-V, we even have an organization called RISC, RISC-V Software Ecosystem, that will be developed or applied to many kind of general purpose AP application. So my conclusion is that the opportunity for all of us is leveraging RISC-V plus AI plus Taiwan. Allow me to say that is the main theme of today's conference. And we hope that, like I said in the beginning, please leverage the semiconductor industry strengths Taiwan has, and leverage the standard of the open standard of RISC-V that to reach your success. We already see the successful result achievement RISC-V already set, and now it is one of the 3 mainstream ISA in the world, and we hope you check out from today's conference, from our pavilion, to see what you can do in the future. And last but not least, I like to have a 1-minute advertisement for RVTA, RISC-V Taiwan Alliance. This alliance still trying to recruit more members. If you are interested, we have secretaries and our CEO Chenny here that you can consult or you can approach me. Thank you.
Thank you so much, Mr. Frankwell, the chairman and RISC-V and Taiwan Alliance, and chairman and CEO of Andes Technology. Thank you. All right, so good morning, everyone. Good morning, ladies and gentlemen. My name is Laras. I'm your host today, and welcome to the Pioneering AI with RISC-V, built on open standards, secure for tomorrow, 2025 RISC-V Taipei Day. On behalf of the organizer, we'd like to extend a warm thank you to all of you for joining us today. Last year, RISC-V Taipei Day was held in Hsinchu for the very first time and received a wide interest from professionals across industries. This year, 2025 marks a decade of evolution for RISC-V architecture and is now showing impressive momentum in the AI SoC space, especially when it comes to chip security. Now, that's why this is the first time ever RISC-V Taipei Day is being held during COMPUTEX. Our goal is to bring together the global RISC-V ecosystem in the broader ICT industry to spark cross-border, cross-sector collaboration aiming to speed up the widespread adoption of AI across the board. Now, first, let's welcome Dr. Alex Wang, the chairman of Taiwan IoT Technology and Industry Association. Please welcome Dr. Alex.
Good morning, everyone. Hi, especially Dr. Frankwell Lin, chairman of RISC-V Taiwan Association, and Mr. Luba, chairman of RISC-V International, and Mr. Wu, representing MODA from the government. And I personally witnessed and sailed through the very rather short but exciting development, which is really a basic golden opportunity for us. The history goes back to 2019. I was president of a Power Chip. I saw the opportunity of RISC-V in open source, and we founded the RISC-V Taiwan Association. And then in that same year, 2019, we immediately held the Taipei, not called Taipei Day, but RISC-V Forum with COMPUTEX right here in this building. And we have significant attendance, but not as crowded, I should say. But the population grows very quickly. Next year, we held the RISC-V Day for the first time in 2020, which was affiliated with Semicon. It's another big show. And then over the 3 years today, well, I should mention last year we did in Hsinchu. And this year we came back to Taipei, and here we are in COMPUTEX again. And over the years, judging from our member attendance, that grows very quickly, as well as sponsors. And it's interesting to see the title theme of this time, which is a pioneering AI with RISC-V. AI is, of course, the word of these days, but in particular, the encroachment of edge AI is very, very popular. So this year, COMPUTEX, I think, theme is AI next. Today, you will hear interesting talks. I'll just give some example. We have brain chip accelerator NPU utilizing endless cores, RISC-V cores, of course. And we have Alibaba Damo I visited Hangzhou. Damo has a lot of talents. So they have this RISC-V chip called Xuantie, very interesting chip. And also there was a talk called Deep Computing. They will talk about RISC-V based 50 TOPS AI PC. It doesn't sound very much compared with cloud computing, which is easily 2,000 or above. And however, for AI PC, as you know, the standard is pretty much Intel 40 TOPS. I think Qualcomm or others may have up to 45, but 50 is considered high. And this area gets very interesting because LLM is, of course, the word these days. Everybody pay a lot of attention. And early this year, suddenly out of the sky, we have the deep seek. And then you can use a Macintosh or a Chromebook to run edge inference, which opens a whole new area of computing. And the RISC-V opportunity, I think, is quite high there. Of course, the buzzword was open source for DeepSeek. In my opinion, it's more like a deep open weight, but it's not important. But open is a word, and I think the deep learn, whether DeepSeek or deep computing or all this, we will have RISC-V, the basis, which takes advantage of open source flexibility and also customization. I believe the area is expanding very quickly. The shipment is already huge. I think Frankwell just mentioned like 1 billion cores in NVIDIA products. And actually, I'm in charge of Taiwan IoT Association. And I think in terms of units, the most shipment in billions are actually in IoTs. Those are small, maybe MCU-based cores. I think the average ASP is probably not high, but the unit is enormous. So we take advantage of that momentum and expand into Edge AI. And I think there's, you can hear today's talk, there will be some cloud opportunities as well. And in the afternoon, we also have I should say Dr. Chih, he's a sort of a public figure, a celebrity host. So he will host the panel discussion today. All the important figures will be helping us to answer questions. So I'm very, as a founding organization, the Taiwan IoT Association, I'm very proud to sit here and congratulate everyone and hope you enjoy the day, and I bid the best success. Thank you.
Thank you so much, Dr. Alex Wang. You may please take your seat. Now, it's our great pleasure to welcome the board chair of RISC-V International, Mr. Lu Dai, on the stage. Ladies and gentlemen, Mr. Lu Dai.
All right. Okay, so, I just back up to my slide. I think a lot of engineers here, so you probably are a fan of Star Trek, so you heard of this word. So my title today is to boldly go where no ISA has gone before. And I want to start with a brief history of RISC-V. I know Frankwell has talked about that before, but I kind of draw that in a time diagram, because as engineers, we like to draw diagrams. It all started back when at the Berkeley in 2010, and when Professor Krista, along with his PhD students, Yunsup and Andrew, they started working on RISC-V ISA. And then in 2011, that first spec was published. And in 2014, there was this famous paper written by Professor Krista and Dave, and on this title of instruction set should be free. If you haven't read that one, it's a very short read, but that kind of talk about our philosophy behind RISC-V, and I think it will be a worthwhile thing for you to read, and it also identified a few technical targets that we started when we work on RISC-V. And then in 2015, we had the RISC-V Foundations, and back in 2020, the RISC-V Foundation got reincorporated in Switzerland, and it's now what's called RISC-V International. And in 2023, we have surpassed 1 billion SoC shipped. As you know that within the SoC, there are many processors nowadays, and there are quite often there's a multiple RISC-V in there. I think one of the slides that Frankwell shared that NVIDIA themselves in 2024, I believe, they shipped 1 billion core. So obviously this 1 billion SoC has a lot more cores in there. And now the estimate for this year, I think all the estimate, if you're only looking at less than 1 year, they tend to be very accurate, right? So the estimate for this year is 2 billion shipped. So we are coming a long way now. So what we believe for RISC-V, and we believe, we need to be able to access, it should be a free to access, free to innovate, and free to customize. So when we said, what about an open instruction set? Open instruction set means everybody who wants to access the instruction set, they're able to do so. And also, because it's open, you can innovate without any barriers. When you're trying to innovate and add things, quite often you got limited by all kind of IP restrictions and licensing restrictions, and we are not limiting you with that, with our open standards. And because of that, we build a very collaborative ecosystem, and with all those collaborations, we're able to innovate more. And that allows us to build a much wider range of applications. So, our advantage, I say it's a future-proof innovation because RISC-V instruction set is one of the newest instruction set architecture. And we are ready, not just for now, but for the next 50 years. And as it's an architecture, it is scalable and modular, so you can fit the RISC-V instruction set for any of the processors from small to big. And because we are also customizable and extensible, you can also add additional instruction sets, additional instructions, so that you can make it more efficient for your specific application, specific needs. And it is an open and global standards, means that we got supported across the globe. It is not a proprietary instruction that is only used by a few, and it is actually supported by the global community and also strengthened by the talents from across the world. And as we mentioned before, as a royalty-free instruction set, that free access allows to foster a very cost-effective innovation and a broader adoptions. So how have we done? We have a very rapid membership growth. It shows that a lot of people are interested. As we have seen that in the conference, we have a membership, we have growth of conference attendance. We also have a growth of our official membership. And we have a cross-market deployment, and RISC-V processor has been used from the small chips to the bigger chips. And we continue to have technology innovation. So I have a few diagrams to show. So as you can see from the top diagram, this is our membership growth. And on the upper left-hand corner, this is the membership growth when we were still called RISC-V Foundations. And on the right-hand side are the membership growth since we become RISC-V International. As you can see, the membership growth is very rapid. And our share of SoC start has also been growing very rapidly. Now, on the lower right-hand corner, that graph shows the up and down kind of diagrams. So these are the additional features we've been adding to RISC-V instruction set, which is what we call extensions, right? These are the additional instructions. Now, as you know, that as engineers, we have tape-out schedules, and as the spec writers, you also have a target date. So from year to year, so the diagram may not show a very consistent one, but what you can see is we're still adding a lot of features, and it is not slowing down. So what could we become? I think a lot of people talk about AIs for this conference, but when we first started RISC-V, you can see a lot of the companies, they are on the vertical front. When I say vertical, that means you build your cores, you build your chip, and you may also build the application software along with it. And because of RISC-V's open architecture, it allows you to innovate and allows you to add your special sauce to your chip. So it fits very well for a vertical type of scenario. But it's also fit very well for AI and security. I think our previous two speakers are already talked about those two areas. One of the common theme about AI and security is AI. A lot of people want to show some differentiations in their algorithm and security. There's a lot of places you want to have some specialized security features so that you have your own sovereign control of your secure processors. And for RISC-V to be customizable and extensible, it fits those very well. Now, because of that, it also allows you to fit into a custom silicon environment. So there are people who are doing mass market merchant silicons, and there are also users of those merchant silicons. They want to have some special tweaks of it, and that becomes a custom silicon. Now, if you want to do a custom silicon with RISC-V's ISA, it makes it a lot easier to do that because of our customizable and extensible. So in the end, we can allow a kind of an end-to-end solution to allow the RISC-V to be applied to any market. And so how do we get there? I think for our RISC-V to be successful, one thing we want to keep on remembering is we need to stay customer focused. RISC-V came from a rich academic background. And engineers like to innovate, but the one thing we want to kind of remember is build what your customer need, not what your own heart desires, right? So ensure, like for example, our profile aligns with the customer requirement. And then, really prioritizing the customer feedback. Listen to what your customer is telling you, and especially listen when your customer complains. And that's a very important thing to do. And we need to do a frequent survey, and we need to ask the right questions during the survey. And then we create the solutions that the customer needs, and think a few steps ahead of your customer. When we build these things, think about if I add these special features to our ISA extensions, this will enable a new capability for our customers. And so here's one diagram. So for example, this is our RVA23. I think I'm not going to go into any details. I believe there is a more detailed presentation later in the day on this profile. And I just want to mention that our profile has the mandatory extensions, and there's localized options and development options. So we kind of categorize our new features into those kind of bundle, and within the bundle, we have the separation of mandatory one versus developmental ones. That allows us to deploy our features more effectively. So one thing that I want to point out for this diagram, it looks like a simple diagram, but if you look at the chart, on the right-hand side is our membership. This is a breakdown of our membership. On the right-hand side is the research institutions. As you can see, RISC-V membership is still very heavily dominated by research institutions, which is a good thing that we are still creating a lot of features. And the purple one is a software companies. And it's also very good because you need the software to help you deploy your hardware. But one thing you can look at that there's a lot of those areas of the low bars, and the one that we are a little bit concerned and we do want to improve on that is on the chip and system side, because there are a lot of companies out there, especially on the system side, right? And as I walk the COMPUTEX floor, I saw so many ODMs and OEMs, and we want those people to be our members because they are the users of RISC-V. So we want to recruit more user membership. And that comes to my next point is we want to be a developer-first mentality. When I say developer-first mentality is we want to make sure our spec is easy to use, it's clear, so you can actually read the spec and understand it. Because when we have the new people adopting these specs, they may not be your CPU expert, they may not be your PhD students, so you got to have the spec written in a way that those people are not familiar with the RISC-V CPU can still deploy that. And we also, in order to drive the adoption, we want to have a compliance certifications so that when people, one of the advantage of RISC-V is you have multi-source IP, but one of the challenge about multi-source IP is how do you ensure all those IP can work across the board, they can be compatible, right? So we want to drive a certification program. And along with that, you have your typical CPU needs of a golden model, an instruction set simulator, all these things to help ensure your compliance certification will work properly. And then also to make sure we have a backward compatibility versus legacy ISAs, so that to make sure our users, when they migrate, we make their life easier. The other point I want to point out, in the end, how do you sell your chip, how do you sell your CPU is the PPA matters. You got to have a good product, right? I do want to emphasize on the high performance side of the RISC-V. RISC-V is actually quite successful on the microcontroller side already. But on the high performance side, we are still just starting. The high performance implementation really attract a customer interest. And when you have a successful PPA and you start to lead, you have a lot more market visibility. Press coverage, like to emphasize on the high performance side, right? And enhancing performance and continuing enhancing the performance directly improve the customer satisfaction, and that will basically allow us to stand out in a crowded market. In conclusion, I want to say the RISC-V ISA, as an architecture, it is a very well-designed architecture, and it's open access, has a lot of benefits that will benefit everybody. We are very well suited for the future of computing, including all applications that you can think of now and the applications you haven't been think of in future. And I want to conclude with this last slide is, we have limitless possibilities, and I want to borrow this line from the paper that I mentioned that was written by Professor Krista and Professor Dave, and that just as Linux has become the standards OS for most computing devices, we envision RISC-V becoming the standard ISA for all computing devices. And I welcome you to this conference, and I hope you enjoy the rest of the day. Thank you.
Thank you so much, Mr. Luda, for your wonderful sharing. You may please be seated. Next, we will have Dr. Charlie Su, the President and CTO of Andes Technology. He will be sharing us empowering innovation in modern computing with RISC-V. Please welcome Dr. Charlie Su.
Good morning, everyone. So today I'm going to talk about 4 key technology to empower modern computing using RISC-V, in particular Andes RISC-V. So first, a quick introduction of Andes technology. So we are a pure-play CPU IP vendor for over 20 years. So we went public in 2017, and in the past 2 years, we were rated by SHD Research Group as a leading RISC-V IP market share leader. So Andes has been playing a leading role in RISC-V International as well as RISE. We are the founding and premium member, and so running the board and also joining TSC and task group. So Andes had over 30 RISC-V processors already, and one of the most leading thing among RISC-V companies is that we have over 16 billion SoC shipped by our customer. So our product has been from endpoint, edge, all the way to the cloud. So we're going to talk about how we enable those with 4 key technology. So the 4 key technology I'm talking about driving modern computing is first, compute acceleration, especially AI machine learning. So we see from the large language model to robot to others, and also embedded and real-time processing, which pretty much go everywhere, not just microcontroller. And also application processing, where you need to running application on top of rich OS, or kind of Linux flavor, and also even RTOS. And last but not least, security and functional safety, actually another dimension which pretty much used by all the above technology together. So just to give a couple examples, today most SoC will use actually one, at least above one technology. For example, SSD controller would need to use embedded real-time processing technology, but also security is very important there. And if we talk about AGI accelerator running some application as well, it pretty much need all the technology I talk about together. And there's other example, so like powertrain SoC or application processor. So following, we're going to focus on those 4 key technologies. So let's first starting from large-scale AI machine learning. So Andes has quite a lot of customers in this area. So Meta MTI is the major example there. And also we have quite a few customers using SRAM-based computing memory to do the matrix multiplication. And then the rest based on RISC-V to form that. And also the customer doing AI SoC for server, for cloud, and using photonics for their AI accelerator, but need to couple with RISC-V and also AI accelerator for others. So large-scale AI machine learning model, basically we can summarize in the typical SoC architecture we call C of PEs. PE is a processing element, so they are mesh connected or multi-clustered. But the core of computation is happening on the PE. And where the Andes core and also the typical RISC-V processor can play the key role in the PE. They can start from the simplest one, but they need to have very efficient scalar code to control all the custom accelerating hardware, either vector, GPU, or matrix multiplication. But they can go one step further using the RISC-V's vector processor, where we have this vector extension and coupled with their matrix multiplication and also all kinds of nonlinear function. But the Andes offer Andes custom extension based on RISC-V's kind of framework. So we do have a lot of customers using Andes custom extension for vector instruction to create a nonlinear operator together with our vector processor. And RISC-V also start to kind of task group have been discussing about all kinds of different ways to implement matrix multiplication into RISC-V architecture. So we also had the processor to incorporate that. And so in addition to that, most of our customers would use our Andes custom extension, we call ACE, to control their hardware engine together so that everything can work efficiently. And also the AI compiler can kind of run in from top to bottom. Andes, let's give the example using Andes' latest RISC-V vector processor, so X46 MPV. It's built on the success of its previous generation, 45 MPV. So it doubled the core count from 8 to 16, and also increased the vector length, and it boosted the most important vector instructions, and also enhanced Andes custom extension for both the scalar instruction and also vector instruction. And then the other one is certainly we talk about the matrix extension, matrix multiplication. But also very important is memory bandwidth performance. So here we increase the load to able to support a dual load either in the dual low and or one low, one store for vector or scalar instruction. It also support private L2 for the flat memory programming. But most important, most of our AI accelerator customer use is something like we call HVM, high bandwidth vector memory, which allow you to have multiple outstanding requests and go with the data coming back out of order, because you're going to have many access content to your memory bank there. So out of order return is possible, and you have to support that. And for that, NDIS also offer the HVM controller so that we can have up to 16 46 MPV instance, and also together connect to the external DMA to kind of go to shared memory so that they can exchange data efficiently. Right, so on top of that, so NDIS has this we call NDIS AI runs everywhere. NDIS Air is the end-to-end solution to tie everything together. So from the top, we can take AI model and go through optimization, conversion, and all the way to generate the instruction to execute on our RISC-V processor. So be it AI compiler, like based on MLIR or TVM, or we have a LLVM enhancement enablement package for customers to do further optimization, or AI compiler based, AI interpreter based, like TensorFlow or SQTorch or Llama CPP. So we can have that flow kind of already go through. And in addition to that, we have this our NN SDK. So we will do optimization at the graph level and also do backend optimization. And that kind of match to our library for the bare metal, like NN library, or we're using the XNNPACK to kind of generate the optimized kernel to run on our hardware. So the underlying hardware can be vector processor and also or the RISC-V DSP processor. And we also have NDIS AI accelerator and DOA there. So it's kind of wide range of covering to cover different level of AI computation requirement. So next, embedded and real-time processing. So one of the most important things is the code size in this kind of application. So RISC-V recently has the new 16-bit ZCE extension replaced the older ZVC extension, which bringing about 2.7 code size reduction. But NDIS being along the industry for quite some time, so we bring the previous pre-RISC-V innovation we call V5 extension, especially the code dense to the table. So that can actually reducing over the ZCE with average about 14% further reduction on top of that. So the benchmark we use is from the multi-megabyte benchmark like SPEC, like CSIPE, like Embassy, to a couple hundred kbyte code, like audio codec, Bluetooth stack, to like sub-100 kbyte benchmark, like Embassy IoT. And certainly RISC-V not stopping here. There's an ongoing task group called Scalar Efficiency, continue to looking for further code size reduction. So code size is very important, especially you have the code need to be burned into the ROM or embedded flash, that kind of eating into your silicon real estate. Right, so next important thing is in those real-time embedded system, there's a lot of hardware module, and you want to have very efficient control and access to those units. So aggressive multiple outstanding access, especially write to the device space with a descriptor, so that your hardware module can kind of kick off and start. So that's very important. And our 40 series is very aggressive on that. We can support up to 128 outstanding access, even though it's in older processor. And some of our customers go a step further. They're using NDIS customization instruction with a custom port to direct connect to their critical hardware module. So they don't need to go through bus with bus contention to slow it down or introduce unpredictability. So that's very important for real-time system. So NDIS custom extension is supported by pretty much all of NDIS cores. Now, in the real-time system, interrupt is certainly very important. So for the single core level, RISC-V has this click, which we support that on our COMPUTEX series, the small core. And for the SoC using multiple RISC-V cores, RISC-V has this PLIC, platform level interrupt controller. And this, on top of that, this enhance it with vectoring and also priority-based preemption. So that is supported by all the RISC-V core. And some customers want really have very short interrupt latency, so we introduce our own extension with shadow register. So when you go to interrupt handler, you don't need to save any register. You can start to execute your interrupt handler right away. So simple extension, but very effective. And also, there's a quality of service matter there for real-time system. So for NDIS, our share cache has this capacity partition. So so you can partition your, for example, you have a 16-way share cache. You can partition by a 4-way. Each 4-way go to one core. So if you do that partition, it can produce like 30% boost of internal memory copy performance. Compare if you have all the core sharing all the ways. They're going to contain a lot on the share cache. All right, so general purpose application processing. So here I'm talking about using it as main processor to running all kind of application. I think in the short term, RISC-V is going to have this on AI, machine learning, edge server, multimedia, networking, industrial. In the longer term, we're going to cover all the personal computing devices like phone, PC, tablet, and so on, all the way to server. And to enable that, we need all the ecosystem support. So RISC-V already reached RVA22, RVA23 profile, and with all kind of Linux distro already supporting RISC-V. So like you can use Android AI, AOSP for multimedia, and OpenWRT for networking, and also Debian for industrial application. And certainly RISC-V software ecosystem, which and this is the active member of that. So we are actively continue working on this to make it even better, along with the development of all those software. And certainly with the ecosystem, like Luba already mentioned, so it still comes down to PPA. You need to have high performance Linux capable processor there. So for this, and it's a roadmap for it. So we already have X65. There's quite a few customers using in different applications. And we are working on X66, which is RVA23 compliant core. And in particular, we're adding a vector processor, which was sharing the same functional unit with a 14 point. So you can have 1 pipe or 2 pipe. And also, we already the target is to getting like 15% performance over X65 to get into 10 spec int 2006 per gigahertz. And we already on top of that, we already seeing that 20% higher memory bandwidth for based on copying. And we have higher performance on top of that on the next one, X67, and on the low one based on this reduced pipeline, but with more power efficiency for X63. But we have another different category product line is under development. We call Cusco, which is 50% and to 2x performance over X66 based on its 6-way to 8-way out of order processor. So it's configurable, and it's based on a unique patented time-based scheduling. So we hope to talk about more detail in the coming hard chips. We already get a paper get accepted there. Right, security. So RISC-V security is one of the hot topics in RISC-V. We have a lot of subjects there. So from control flow integrity to memory tagging to table-based protection attributes to countermeasure of side channel attack and so on. But the most common question we get asked is, does RISC-V support trust zone? Usually my answer is, no, we don't have trust zone, but we have something better. But anyway, trust zone is ARM's trademark. So what it README is custom read one is a T, a trusted executing environment. So looking at the core integrity, data integrity, and data confidentiality. For this, NDIS has a T solution based on our ND-centric framework based on RISC-V. So on the hardware level, we have security platform where we have RISC-V processor with ePMP, and also with we also have IO-PMP module to connect it to the important SoC module there. And based on that, we have ND-centric secure boot to boot your boot code. And once your boot code gets booted, you can bring up the secure monitor of your choice, depending on your application. And secure monitor is to securely loaded and isolated different zone, and also to manage the communication between that. So if you're running RTOS or bare metal, NDIS offer MCU-T to kind of serve as secure monitor. And if you're running Linux, there's an OP-T, which is open source. NDIS already working on that actively, and we're driving that in the RISE and working with other partners in the RISE to make it upstream. So RISC-V's answer to trust zone is hardware level, ePMP and IO-PMP. In the software level is MCU-T or OP-T, depending on your target application. Right, and let's also talk a little bit about functional safety. So NDIS had this safety enhanced series we call SE, but we come a long way. We started from ISO 9000 about 15 years ago, and then we have 26262, a development process, get certified in 2020. And then in the past 3 years, we have 3 core get certified. So we had 2 core certified for COB, and recently we have the 45 SE get certified at SCOD level. And it already has a customer using in the chassis control and also powertrain control. And going forward, we're going to have functional safety certified core on the COMPUTEX series on our 64-bit with hypervisor, vector, and multi-core. And also in a very high-end one, out of order core, we're going to have a certified version as well. So here, RISC-V offer one architecture help for this. We call RERI, Race Error Reporting Register Interface. All right, so all the above I talked about couldn't be possible without the software development environment. So NDIS Tsai is something we've developed over 20 years. So it has a bunch of important features from optimizing compiler to the linker script editor to the advanced SOC debugging, functional profiling, code size analysis, simulator, and also RTOS aware support. And so those are kind of come standard with our NDIS. But there's also some advanced feature which need to separate licenses, like auto optune, which can automatically tune your compiler flag for your application, and the system simulator, and also performance visualizer, pipeline analyzer we call NDIS Clarity, and certainly NDIS custom extension, which we talk several times about it. So in closing, RISC-V is being efficiently addressed 4 key technology in modern computing. So from safety, security, application processing, embedded in real time, and AI machine learning. And NDIS has leveraged those to lead the RISC-V IP shipment. But how does NDIS achieve this? So we build on top of RISC-V. So NDIS innovates unique custom extension, which the RISC-V architecture allowed. And we also offer comprehensive hardware software solution. And we continue to broaden our product portfolio. So please come join us in seizing the opportunity in modern computing using the RISC-V. Last but not least, in another 3 weeks, we're going to have our annual RISC-V Con held in Hsinchu. So the subject is repioneering the future. So everything I talk about going to go into more detail. So June 10th, Tuesday, welcome everyone. Thank you.
Thank you so much, Dr. Charlie Su. You may please be seated. Now, follow up. Let's welcome Mr. Luke Yen, the fellow of RISC-V CPU and Machine Learning Architecture of Tenstorrent, who traveled all the way from United States. So the topic today is scaling open compute, RISC-V chiplets, and the future of AI and robotics. Please welcome Mr. Yen.
Thank you. Good morning. Today, I want to draw your attention to three themes that I'll be discussing: scaling, open, and AI. As we enter a new era defined by AI, three concepts come together in a critical way. We have seen explosive growth of AI workloads, and we must work together to scale our hardware capabilities like never before. We must do this together as a community. Open compute technology, like open architectures like RISC-V, and open ecosystems have emerged as the only sustainable path to scaling hardware efficiently at the pace AI demands. This is where RISC-V plays a pivotal role. We're currently living in an era, in a very exciting time, where artificial intelligence permeates our lives. AI shapes the way we work, how we plan, make decisions, and even how we create new things. AI will become personalized and ubiquitous, serving our daily needs across every aspect of life. This requires a diverse landscape of silicon, embracing architectural variety, heterogeneity, and composable design. We believe at Tenstorrent this is a very historic opportunity, and we are in a golden age of silicon diversity. As Lou and others have talked about before, open architectures like RISC-V is foundation for supporting this silicon diversity, and it achieves the goal in 4 different ways. First, it's scalable. Designers can scale the hardware up and down depending on the workload requirements, from embedded devices to high-performance servers. It's expandable. Designers can quickly add custom extensions to tailor the architecture to specific application domains, quickly enabling innovation. It's efficient. Hardware can be optimized for particular applications, improving performance, power efficiency, and cost effectiveness. And finally, it's stable. Because it's an open ISA, contributions can be made from multiple vendors, strengthening the ecosystem and improving supply chain resilience. Tenstorrent has been building a broad portfolio of chip technologies designed to scale across applications. At the core are 2 key compute IPs, our AI accelerators and high-performance RISC-V CPUs. Surrounding these are critical subsystems, including memory and fabric interconnects, I/O, power management and security, RAS, debug, and system management technologies. We've also developed a chiplet architecture, which I'll talk about shortly, that allows modular scaling from edge to data center, enabling flexible system designs. These technologies are powering our data center products, automotive compute platforms, and our Japan AI Design Center partnership, where we co-develop advanced AI solutions with them. In the next section, I'll share how Tenstorrent is developing diverse high-performance RISC-V technologies. A successful open CPU architecture requires more than openness. It must deliver cost-effective high performance. High-performance CPU implementations are critical for enabling demanding workloads in data centers, automotive systems, and robotics and industrial applications. They also form the foundation of a strong software development platform, allowing advanced compiler optimizations, in-depth system software tuning, and real-world application performance to be optimized to its full extent. Without a performance CPU, even the best architecture cannot succeed in real deployment. Let me now discuss our Escalon high-performance RISC-V CPU, which delivers best-in-class performance. Escalon is now approaching the final design stages and features 18 spec-int per gigahertz performance. It's an 8-wide decode out-of-order superscalar architecture. It supports 3 load store units, 2 branch units, and 2 256-bit vector units. Escalon has been built to power next-generation compute workloads across data center, AI, and automotive technologies. The Escalon core will be deployed in Tenstorrent's Athena CPU chiplet, which integrates 8 Escalon cores in a cluster, 16 channels of PCIe Gen 6, 2 channels of LPDDR5X memory, and Athena will be used in 2 key ways as part of Tenstorrent's heterogeneous AI products, which tightly couples AI accelerators along with the CPU chiplet, as well as a standalone CPU chiplet for general purpose compute applications. This flexible deployment showcases how high performance open cores can serve multiple markets through modular chiplet designs. As you can see, Ascalon is an advanced stage of development. This is the physical design diagram of our 8-core Ascalon cluster. Key features include 8 Ascalon cores, as well as 12 megabytes of shared L2 cache. This design has been performance correlated to deliver 18 spec in per gigahertz, demonstrating that RISC-V cores can meet top-tier performance targets in silicon. Tenstorrent is also committed to delivering world-class CPU performance with a comprehensive roadmap. We will continue developing Ascalon performance and improving performance by 10% annually, ensuring it remains competitive across multiple generations. In parallel, we launched a new CPU development team 6 months ago, targeting a next-generation CPU core with 35 spec in per gigahertz performance target. If introduced in 2027, Calendor will be amongst the highest performance CPU cores in the industry, built on open architecture and designed for the most demanding workloads. This is some more detail about our Calendor. We're pushing the boundaries of open CPU performance with our next generation core targeting 35 spec in per gigahertz in spec 2006, 3.5 spec per gigahertz in spec 2017. And it will be compliant with RBA 23 plus features. The front end will support advanced branch prediction with support for 2 taken branches, a decoupled front end for deeper pipeline efficiency, and integrated micro-op cache for high-performance instruction delivery. The mid-core features 16-wide decode for massive instruction throughput, register file sharing to improve resource utilization, and a 1K reorder buffer for deep out-of-order execution. There are 6 wide load store with large load and store queues for memory-intensive workloads, 8 ALUs and 4 branch units, 4 256-bit vector units, and 4 FPUs for floating point workloads, and a dedicated matrix engine for AI and HPC applications. This design represents one of the most aggressive and advanced RISC-V CPUs ever developed, showcasing what open compute can achieve at the cutting edge. We're extending Ascalon into the automotive domain with Ascalon Auto, designed to meet the ISO 26262 functional safety standard. Key functional safety features include dual-core lockstep with time disparity detection, bus protection for both coherent and non-coherent traffic using CRC or ECC, ECC protection for the L1, L2 caches, integrated RAS, reliability, availability, and serviceability, and fault controller, dedicated safety debug bus, and support for software test libraries. Its performance targets include up to 830 spec 2017 at 2.25 gigahertz per cluster, as well as 17.34 DMIPS per megahertz. Ascalon Auto brings high performance and robust safety to automotive, robotics, and industrial systems, delivering RISC-V compute where reliability is mission critical. Next, I'll explain how Tenstorrent leverages the use of chiplet technologies to tackle the computation demands of AI while promoting openness in our community. Tenstorrent is developing chiplet technology as a key enabler for scalable and modular silicon design. We design chiplets for our data center products, and this is also a critical part of our automotive strategy. Chiplets allows us to mix and match IP blocks optimized for different workloads and domains. Looking forward, we also aim to open our chiplet compatibility technology, enabling different organizations to build composable silicon. This will foster greater silicon diversity, reduce cost, and accelerate innovation across the ecosystem. Our open chiplet architecture defines interoperability across 5 key layers, enabling true composability across vendors and technologies. The first layer is physical. Here we aim to standardize bump pad layout and signal integrity. The second is transport, having common electrical and signal specifications. Third is protocol, having consistent data transaction formats. Fourth is the system layer, which includes inter-chiplet coordination, power management, and coherency. And finally is the software layer, which has unified interfaces for drivers, firmware, and system software. This layered approach allows organizations to design, share, and integrate chiplets with confidence, supporting a scalable and diverse silicon ecosystem. This slide illustrates an example of how open chiplet architectures enables modular silicon design. At the bottom, a base die provides both GPU and I/O connectivity. Surrounding this is a CPU chiplet, AI accelerator chiplet, and memory chiplet. With an open chiplet architecture ensuring compatibility, each company can focus on its core competencies to build the best-in-class chiplets. This approach drives innovation, improves reuse, and reduces cost, unlocking the full potential of heterogeneous computing. This slide shows how chiplet technology enables scalable compute architectures to support varying levels of autonomous driving. At the low end is the level 2 autonomy, which could be enabled by a smaller configuration with CPU plus a basic AI chiplet. Then as you move up to more compute, more capabilities, there's level 3, which adds a high-performance AI accelerator with more memory. Finally, when you reach the full level 5 autonomy, this will probably integrate multiple high-performance CPUs, AI chiplets, and large memory subsystems. By leveraging open chiplet architectures, OEMs and Tier 1s can scale designs based on performance, safety, and cost targets, without redesigning the entire SoC. This modularity accelerates time to market and supports the diverse compute needs of modern automotive systems. This slide illustrates how chiplet technology enables the design of heterogeneous AI compute platforms, which are essential for future neural-symbolic AI workloads. So what is neural-symbolic? In this architecture, this SoC integrates neural processing chiplets for deep learning inference, symbolic reasoning chiplets for logic-based AI tasks. And this includes both symbols as well as reasoning support. In addition, it has high-performance CPU chiplets for orchestration and general-purpose compute. A common interconnect will connect all these chiplets together and having a base die to unify communication. Using an open chiplet architecture, as I described, each compute domain is optimized independently and integrated seamlessly, paving the way for next-generation AI systems that can combine both learning and reasoning on the same SoC. So let me recap what we talked about this morning. AI will be both personalized and ubiquitous. AI compute requires diverse silicon to satisfy its computational needs, which will improve and increase over time. I presented Tenstorrent's high-performance CPU roadmap, with our cores rivaling the best in the world. Our open chiplet architecture enables composable systems and multiple vendor integration. Together, these pillars define our mission and an opportunity to build the future of open, scalable, and intelligent compute. Thank you very much.
Thank you so much, Mr. Yan. You may please be seated. Now, please welcome Mr. Luba Tang, the founder and CTO of Skymizer, to come on the stage. And his presentation is Skymizer HyperThought, Hyper-Treating Language Processing Units for Large Language Model. Please welcome Mr. Luba Tang.
Hello, everyone. Good morning. I found that we are in a big trouble. I am become a gatekeeper between Earth and the launch. So now I will try to speak faster, and if you cannot catch me, no problem. We can discuss offline or even discuss about LN when in the launch. Today I will present HyperRO. It's our new product. It's a kind of language processing unit. Okay, the first I will try to introduce Skymizer. Actually, I started Skymizer about 12 years ago. And in the first 4 years, we gained 0 revenue Yeah, amazing, zero revenue. Because my product is Chih and Chih purpose compiler. I'm so sorry, Chih and purpose compiler is very hard to sell. So about 6 years ago, we do a good pivot. We pivot to a business model to make an AI compiler, and the other business model to make a blockchain virtual machine. And with a lot of luck, both business models succeed. So I spent off the blockchain business and sold it out about 3 years ago. And let Skymizer keep it on making the AI compiler. And I find that there are some my customers sitting over there. And I have to say sorry because we do another pivot our business model to making the LN accelerator about 2 years ago. So we are stuck in making an accelerator. So I really have no human resource and time to make a compiler anymore. And today I just want to share our perspective why we start making the LN accelerator. Yeah. And of course, in about 3 years ago, OpenAI announced the ChatGPT, and all of you must use it to make GPFi images to burn a lot of GPU. And why LN is so important for the semiconductor industry, because it shows the two very important features. The first, it is a new interface between human and the machine. Now you can just use your natural language to control the machine. And more important, it is also a new interface between machine and machine. There are a lot of cases and studies to make two AI, and each AI have its unique function. And those two AI doesn't know what they can do for each other. And you just put two AI there. They start to talking and they make a new language. Eventually, they can know how to use each other's and to do some, to complete some humans instruction. So LN is also a new interface between machine and machine. And then why it's so important? Just remember the iPhone momentum. For everyone, we have 4.8 computers around us. You have one computer in the office, one computer in your home, and you have a phone, and you have a computer in your car. So on average, everybody in the world, they have 4.1 computer in the world. And the iPhone is only one of 4.8. And it expands the semiconductor industry by more than 2 to 3 times over the past 2 decades. And for LN, as I mentioned, it's a new interface between you and the machine, and between machine and the machine. So just think about that. If all the computers, they need to communicate with each other, there must be 2 new processors running an LN in the SoC. One is talking to you, and the other is talking to the other machine. Okay, that will expand the semiconductor industry more than 100 times over the next 2 decades. That is why when OpenAI announced its ChatGPT, almost all the ICT house I know start to making an LN processor. Yeah. And our product called Hayter, of course, that is our 3rd generation product. It is a kind of hyper-threading language processing unit. And I will try to tell you how effective, how high performance, and how is scalability, like scale out and scale up, and how we handle the security issue in the LN. And then we define a new instruction set architecture. We call language instruction set architecture Lisa. It's a very beautiful name. And this is our 3rd generation. Yeah. And why Skymizer switched to from making compiler to making the hardware? That for many of us, from making a software, jump to making hardware, that is really a big leap. So what we see that function we call arithmetic intensity. Here there are many computer architecture architects here. So I just want to mention this very simply. That means how many arithmetic instructions over the memory operator. And for many traditional architecture like CPU, the arithmetic intensity is about 2 to 8. And its bandwidth requirement is about 5 gigabytes per second. But for GPU is designed for 300 arithmetic intensity, and its bandwidth is target on more than 100 gigabytes. Sometimes it's target on terabyte. And for DSP, we have very long instruction word, and it's target on about 300 arithmetic intensity. But its bandwidth, just like the CPU, is about 8. And we do a lot of experimentals and do a lot of study. You find that we get the same result before this paper published. In traditional CNN architecture, the target arithmetic intensity is about 200 to 300. That is why GPU is so effective. But for the LN, especially the decoder-only LN, the arithmetic intensity actually is only 2. That means for every data, you just need one add and one multiply operation to handle it. That is enough. But its bandwidth target, just like GPU, is about 100, even terabyte per second, such very high bandwidth. So we found traditional architecture, they just cannot meet the requirement of LN. So we found we need a new computer architecture. We call it LPU, Language Processing Unit. It targets on very low arithmetic intensity and a very high bandwidth requirement. Yeah, so our principle is try to make the best LPU in the world. So let we see how we measure an LPU. The most simple formula is just like that. Where people measure LPU by its token per second. And the token per second is related to the model size and the bandwidth you have. So from Skymizer's point of view, to make the best LPU in the world, first, we will try to leverage our quantization and pruning algorithms to compress the model size as many as possible. And the second step, if we already have the smallest model in the world, then the next is try to use the minimal number of MAC, use the minimal computation power, let a little minimal area to do the sufficient computation. Then we will try to cooperate with all the DRAM vendors in the world like PSNC or like Peacemaker to make sure we have very high bandwidth DRAM. So the formula is very simple. The first is try to use our compiler and our architecture ability to squeeze the model as small as possible. Then use the best technical node or the cheapest technical node to make the area and the power requirement as small as possible. Then cooperate with all the memory vendors, try to enlarge the bandwidth. That is our formula. Yeah. And this is when we are talking about this is one of our achievements. Okay, because we do the AI compiler for many years. Actually, there are some of my customers sitting over there, and we almost collect all the quantization and pruning algorithm in our tool chain. There are more than 40 different algorithms here. And we invent a new AI. Unfortunately, it's not a transformer, but it's still AI. Try to figure out the combination of all the algorithms to find out the best formula to compress the weight. So give us a LM model the weight is very big, then we will try to separate the model into thousands small pieces. And for each pieces, we'll find the best algorithm to shrink the size of the entire model. And this is our result. Comparing with, to my best knowledge, we still the best solution in the world. Compared with all the academic solution and the open source solution, I just use Llama CPP as one of my competitor, the open source version. And our worst case is better. Their better case compared with our worst case, I still outperform they about 10% model size. And when I try to squeeze the model, make the model more smaller, then I can save the different size more than almost about 20%. And when we are talking about perplexity drop, why perplexity drop is so important? Because it represents the smartness of the model. In our worst case, our perplexity drop is less than 1%. And in our best case, the perplexity drop is a little slightly bigger, but it's still less than 4%. And for the open source models, their best case is more than, their perplexity drop is more than about 8% to 10%. So far, until to my best knowledge, our weight compression ability is still at least at a pioneer position in the world. And for the other hand, we have ability to compress the KV cache. What is KV cache? KV cache represents the short-term memory of the ALM. And when we have this result, we are the only one, the only group who can do the KV cache compression. And for now, there are several academic groups and open source projects. They also have the same ability, but we're still at the pioneer position. We can compress the KV cache to different bits, just like 8-bit, 7-bit, 6-bit to the 4-bit. And comparing with the open source Llama CP++ project, they only can compress to the 8-bit. So we can save before the compression. The KV cache you may need 2 GB to store the KV cache, but after our compression, we only need about 100 to 200 megabytes to save the KV cache. And to my best knowledge, we are the only practical solution to do the KV cache compression. Okay, and as I mentioned before, to try to achieve the limit of the performance, to get the best formula, we try to use less number meg as possible. So in this system, we try to push both DRAM bandwidth utilization and meg utilization to the limit, and both to such kind of utilization is higher than 90%. That means I rest only very, very small run to my competitor. Actually, we are very, very close to a theoretical solution. Yeah. Okay, this is just a comparison about all the other chips, available chips. And if we try to measure the performance in the token per second per TOPS, then we'll find we only use 0.5 TOPS and get about 30 token per second. But compared with our competitor like this one, their solution, they have 100 TOPS, but they can get only 11. And for some smartphone solution, although they have about 30 TOPS, but their token per second is still, we still outperform them. And you can analogy about the TOPS to the area and the technical node. And in this case, actually we are making the reference chip. In this case, we use only TSMC 28 nanometers to get such kind of high performance. All my competitors, they are trying to use Samsung more advanced technology node, but I still can outperform their chip. Yeah. Okay. So let me talking about some uniqueness of our chip. The first is the hyper-threading architecture. As we know, Intel, their Pentium 4 Pro become the profound and great product of Intel just because they try to leverage the hyperscaling and hyper-threading and super-scaling in their architecture. And we follow the same idea. We try to design a hyper-threading architecture for multi-core in our system. In such system, actually we can run multiple models simultaneously, and multiple users can get different token string together. And the best is that with such hyper-threading architecture, we can connect multi-core in the same chip. And with such kind of architecture, then we can enlarge the token per second from 30 to 240. As to my best knowledge, that is the best performance so far we do after we do all the marketing analysis. And we have another strength is that because we also have a technology to connect multiple chips together, just like a chiplet. And with such technology, we can enlarge the performance to train all the chips in a chain. Then we can enlarge the token per second to another level. So for our reference chip, we try to put 6 chips in the same EVB, and we can get 1,200 tokens per second in this reference design. And we also, so of course, we support multimodality. And one very unique function is that we support multiple models. What does this mean? That means because we have 8 core in this chip, so you can at least put put 6 different models in the same chip. Let's just think about this case. When you are making a chatting robot, then you need a first model whisper to convert the sound to text, and second model LN to do a reasoning to understand what you are talking and try to respond to you. Then you need the third model Piper try to convert the text to the sound. With these 3 models, you can make a chatbot, and it can listen from you, speak to you, and you can have some interaction with you. And in such kind of design, all these models can run in the same chip, and to do the very different functionality. Yeah. And the last is about security. That I have one customer, they got a problem because in LN actually cache the small memory, short-term memory is very easy to attack for the hacker. Just because many applications, if they use the same model, their cache format is identical. So for the hacker, it can just override the cache to make the application try to do incorrect behavior. The software won't be crashed, but it will start to say some inappropriate words. But without such kind of new instruction set, we try to protect the cache for different processes in the system. They have a different cache format, so that the hacker cannot just override the cache to get the control of the application. Yeah. Okay. This is our new product, HyperRoll. And why it's called HyperRoll? Just because it has very unique architecture, hyper-threading inside it. And with such architecture, we can get very high performance with very good PPAC. And of course, it has the ability to scale out from chip to chip and die core to core. And we also have some security ability to protect the KV cache. Yeah, this is all my talk today. Thank you, everyone.
Thank you so much, Mr. Luba Tang. You may please be seated. Now that wraps our morning session. Thank you so much for all the speakers. Now, before we head into our lunch break, we are having an exciting moment right now. We'll take this opportunity to express our sincere appreciation to Syntronics, a longtime sponsor of RISC-V Taipei Day. Now, today we will have two amazing prizes. The first one is Logitech keyboard and mouse combo. Now, I want to check first. Good morning? Good morning. No, one more time, okay? I know you guys are hungry. One more time, okay? Good morning, everyone? Good morning. Perfect. Now, all the business cards and your handwritten entries already been submitted in our draw box. Now, I would like to welcome Mr. Frankwell Lin, the chairman of RISC-V Taiwan Alliance. Please give applause. Perfect. Now, I will ask first. Hi, Mr. Frankwell. How are you doing?
Pretty good, thank you.
Really good. Now, are you ready to draw our winners?
Let's ask audience, are you ready?
Are you hungry? Are you ready? Okay. All right. Perfect. So you may go ahead, sir. First time is our Logitech keyboard and mouse combo. You may go ahead and pick one business card. Maybe there are some people that are needing a new keyboard, right? Oh, okay. Now please go ahead and call.
It's my colleague from Indies, Warren Chen.
Congratulations. Okay, please come forward. And the gift will be given from Mr. Frankwell. And let's have a picture together. Yes, 2 pieces. Very lucky. Wow, Lao Pan. Congratulations! Wow, such an honor. All right, perfect. Now we have our bigger prize. Are you guys ready? Wow, I see everyone is like, oh yeah, please be me, please be me. And also, maybe the MC? No.
I promise this time it won't be Andy's colleague.
Okay. Make sure, okay? Now, this is for Apple iPad Air. Okay, let's have a look. Ooh, exciting. Oh, no sneak peek. Oh, okay. Oh, this is a handwritten, no business card. Oh, 可以吗? Okay, okay, please.
NYCU 孟雨珍.
NYCU, please come forward. Is there anyone here? Uh-oh. We call 3 times, okay? If there is no person, then we will change. Agree? Okay? 3, 2, 1. Okay, no? All right, new one. Okay. Oh, another one.
陈鑫.
Wow. Okay. Please come forward. Okay. Wow, very shocked. Wow. Congratulations.
Can you tell us where are you from?
NTHU.
From NTHU, Tsinghua University. Are you from Hsinchu? Oh, very lucky. All the way from Hsinchu to Taipei. Thank you so much. Congratulations. All right, so thank you, Mr. Frankwell. You may be seated. Now I know that you guys also want another prize. We make sure that we will begin our afternoon session at 1:30 p.m. So please make sure you return on time and don't forget to provide your business card because we will have another lucky draw. Okay? So if you are not here at the afternoon, I'm so sorry you cannot have the prize. Now, also a quick reminder, we also have a RISC-V Taiwan Alliance showcasing at the exhibition hall on the 4th floor at the booth L0425. All right, so thank you so much and have a good lunch. Good afternoon, everyone. Welcome back to the afternoon session of 2025 RISC-V Taipei Day. Now, we will continue to explore the latest trends and also innovation of real-world application in the RISC-V ecosystem with an outstanding lineup of speakers ahead. Now, let's get started with our first session. To kick off our afternoon session, please welcome Mr. Ruinland Tsai, the chair of System Library Working Group from RISE. To share with us, we also have the presentation Unleashing the Potential of RISC-V through Open Source Collaboration. Okay, let's give applause again to Mr. Tsai.
Thank you. So, good afternoon, ladies and gents. So, my topic today is unleashing the potential of RISC-V through open source and collaboration. And even though RISC-V is a very, popular architecture, and many workforces are donating their powers to the RISC-V, and just like the movie says that apes strong together. But to harness this momentum, we need to break down the things into three categories. First, the collaboration and the community engagement, that we need to do it transparently with the open source community. And secondly is that we need to invest into the software stack fundamentals. Without the healthy substrate, we cannot grow our ecosystem upon it. And thirdly, we need to do the continuous work on software porting and optimization. Because software, if you just let it rot it there, then you won't grow. So you need to continuously donate your either fundings or powers into it to make it healthy. So currently, I'm serving as the System Library Working Group host. And my role is actually can be break down into three categories here as well. That one is that to raise the RISC-V software ecosystem quality. That just to make it run, it doesn't mean it's good. So we need to make sure the quality is the best, even better than other architectures. And secondly, we need to ensure that the RISC-V support is the tier 1. For instance, back then the Rust and like Golan doesn't treat RISC-V as a tier 1, but in the System Library Group, we have constantly emphasized that RISC-V is the key into the future, and we need to ensure that it's in the tier 1 support. And the third is that we need to ask our vendors and our users to adopt the things that we have been created, so we are aligned on the same page and nobody left behind. So how we are working like this? Firstly, we need to work with the upstream transparently, that there's no backgrounds and saying, hey, something like a backdoor treat deals. We need to do it in the open way. And secondly, then we need to coordinate our workforces. No interleaved works, just dispatch the work evenly and to people who are having the interest into it. And thirdly, that we need to bring the open source power. There's nothing more inexpensive than college students. They have spare of time, so we need to bring in the open source powers. And here are the members of the RISE. You can see there are all the industrial leaders. They either donate their fundings into the RISE or donate their work power. Like myself, is actually counted as a full-time employee for the RISE project. And with all these with all these vendors, we share the same goal. We want to make RISC-V a better place and the key instruction set architecture in the world. So currently we have these all working groups like the compiler intuitions. The main focus will be on the LLVM, GCC, and JDBC. We also have a lot of improvements on the LLVM, GCC recently. I like for the BF16 and the RVR24.3, we have the compare and swap instructions, so they can be used in the compiler intuition optimization. And for myself, the system library groups, we have FMPAC. We currently work with the FF Lab to do the H.264 and a lot of codecs improvements. Also the Open Blast and Open DAL and a lot of codecs and libraries as well. And for the kernel side, you can see the Linux kernel is always evolving. We have the hardware probe and a lot of things being used. And Android, if you downstairs have the 4th floor, you can see in our NDIS booth, there's an Android port. So this is also a key point. And performance profile, memorial, and Valgrind for developers to debug the code and have the dynamic translations and instrumentations. And language runtimes and Linux distro distribution as well. That many Linux distribution doesn't treat RISC-V as a tier 1 back then, but now most popular distributions such as Ubuntu, Debian, Fedora, RHEL, many distributions are now treat RISC-V as the first tier. And simulation, the QEMU, Spike, and system firmware like the UEFI, U-boot, and corporate TFM, stuff like that are now already there and running well on many RISC-V platforms. And for dev infra, we also have the board fund that if you don't have the real hardware or you want to test out something that is not publicly available in the open market, we still have the development infrastructure for you to evaluate. And for the secure software, that we also have the working group working on Opti and many other security firmwares. And recently, the most hothead issue is the AI MML, like the PyTorch or the Llama CP, stuff like that. So the most commonly asked working group, the AI ML, that currently we have in the RVI side, the RISC-V International, we have the AME and IME, the attached metric extension and integrated metric extension being on their way to be ratified. But currently we also have the vector, and vector crypto has already been ratified. So there are many ongoing projects such as PyTorch is being it's very intensively being optimized with the vector extension. And enhancing the software ecosystem can also strengthen our RISC-V position in the AI market right now. So just like I said, that making things works, the ports things is just the key start. And it doesn't mean it runs well. So we need to donate our fundings and work into it to make it run better than other architecture. That's the reason why we do RISC-V right. We want to make it better than x86, better than ARM, better than any other architectures. And then we need to optimize with the new extension we ratify and it's like a round-the-round clock. Once there are new extension, new profile being released, we make it work first, and we make it work well, and then we optimize it. So how is RISC contributing? That just like I said in the past, that you need to foster the open source collaboration. You need to establish a dev infrastructure like we have the dev infra working group to have the board front. And third, that you have to activate the border development community to bring in people in. And how do if you are already a member of RISC, then what can you do? The first thing is you need to be a member, First you need to become one of us. Then you can file an official RFP, the request for proposal. For instance, recently, many people are interested in the PyTorch, so they filed the PyTorch RFP. And for many people that are interested in DPTK, so they are filing the proposal for the DPTK. And then, once after the RFP is approved by our RISC board, then you can have the developer incentive program to do the rest. Sorry, this is my mistake. If the board approves the RFP, then it will become the project that will be contracted with partners or be acclaimed by the member. And if you are a third-party individual developers, then we also have the developer incentive program that you can file your project into our our email address and saying, hey, I have done a wonderful thing for RISC-V and I want some money from you. So that's the way to do it as well. And here we currently have 13 active RPs, and here are some of the highlights. For instance, like I said, Go and Rust was once not the part of the game for their developers, but we ensure that they are now optimized by like bit manipulation, vector crypto extension, and it's now the tier 1 support. And for Rust, there has been a very intensive altercation between the Linux and the Rust community. But besides of all the stuff like that, we're currently the tier 1 support for Rust, and many projects like Rust SBI is running very, very well on bare metal. And also we have the RP for the QEMU that back then the emulation for vector and vector crypto is very, very slow. It's like take 13x of the time, but now we cut down it to the half of the time and the half of the memory usage. Also, the RISC-V OpenOCD support is now upstream, and we have the LLVM CI for many optimization paths and stuff like that. For also the compilers back 2017, the performance is now doing very, very well. So here are the RFP highlights we have done. And so to recap, basically the key point is these three. We need to raise the RISC-V platform software quality and to ensure that RISC-V software support is the tier 1, and to align the people to make people share our results. So that's the whole thing. Thank you very much.
Thank you so much, Mr. Tsai. You may please go ahead to your seat. Next, I would like to welcome Mr. Mark Hayter, co-founder and also Chief Strategy Officer of Rivos, to come on the stage. He will be sharing with us the significance of the RVA23 profile and platform specification in advancing RISC-V ecosystem development. Please welcome Mr. Hayter.
Thank you, everybody. I'm going to talk about profiles and platforms, which are one of the ways that we're advancing the RISC-V ecosystem. And I'm probably going to offend a bunch of people with my next slide, because I've almost certainly left out a bunch of logos that should be on it. But if we look at where we've got to with our open ISA, we have a vast collection of people making IP, and we have a vast collection of people making SOCs, some using their own internally developed IP, some using IP from the IP vendors. And this is great. This is exactly what RISC-V was all about: openness and building a broader community. So we should be very happy where we are. There's just one slight issue. It can be very, very scary to software people. So if we look at what we've got in RISC-V, we've got our core ISA, which is on the left here, and we've added to that a bunch of extensions to the ISA, a bunch of non-ISA extensions, and a bunch of software specifications that we've used, and then people are free to push in their own custom extensions. So this is great. This enables the diversity and flexibility that we've been hearing about this morning. But if you're a software person and you see all this flexibility, you'll say, well, what can I rely on being there? How can I write my code if I don't know whether this extensions are going to be supported or not? And the answer to that is what we call profiles. And this is essentially to give certainty to the software developers. That's the whole point of a profile. Give the software developers certainty. And there are various profiles. The particular one I'm going to focus on today is the application processor profile, so RBA. There's also an embedded RBB and a microcontroller that's still under discussion. So RBA gives a set of mandatory use of extensions And so if you are writing code, if you're writing user-level code or hypervisor code for an application processor, and it says it follows the RBA23 profile, you know exactly what extensions you can rely on being there. There's a second thing, which I'll talk about a little later, called platforms. And this is about providing certainty to the operating system and firmware writers. And I'll talk in a little bit about how that comes in. So the profile, and there can be many, but RBA23 is really about applications, and it's broadly applicable across mobile laptops, servers. And if you are writing software and you want to distribute it in an app store, or you want to distribute it as part of a distribution, most likely it's going to be a binary, right? You're not going to distribute something that the end user has to compile. So you have to know what instructions, what directives to give to your compiler. And RBA23 for the 64-bit application processors says exactly what's there. And the goal here is, if you move from one vendor's RBA23 profile processor to any other vendor, your code will continue to run correctly. Doesn't talk about the performance level. Obviously, if you've got a high-performance chip or a low-performance chip, you'll see performance differ, but your code will run, and that's what the profile is there to ensure. The platform level is when you delve one level deeper. So if I'm writing an operating system or doing a Linux OS distribution, again, I want to be able to install that whatever vendor of RISC-V SoC I've got. And so the platform level specification is saying what things must be there that the operating system can rely on. So if we look at this in a server case, since I'm from Rivos and we're doing servers, I'm particularly keen on the server case. If you look at the application layer, as I said, you want to be able to distribute binaries. But if we look further down the stack, we need to know. And if you look at what happened in the ARM server space, and let's learn from our competitors here. In the ARM server space, it was kind of a mess to start with. All the vendors were doing things in different ways. No one had any certainty, and so it was very slow for the whole space to take off. And at the European Summit last week, the service provider Scaleway, who actually have RISC-V available as a cloud service, they indicated that for their first RISC-V, before we talked about doing platform specs, they had exactly the same problem. They went through the list of problems with not supporting what was expected for a server, not supporting the right firmware interfaces, not supporting the right management interfaces. So for the server spec, it's very important that we all coalesce around the same set of features that are needed by the people installing servers. Okay, I'm not going to read through all of the list of new things that are in RBA23, but it's important to understand their categories. So mandatory is exactly what it says. These extensions must be supported by everyone who does the RBA23 profile. There are a couple of what are called localized extensions. Primarily, these are cryptography. So they're sort of fairly complex and potentially large extensions. And if you're selling to a particular region, you may only want to support the cryptographic protocols for that region. So this is why these are localized. You can, if you want a worldwide part, you'll obviously want to put all the algorithms in. if you're regional, you can save some complexity and potentially area by selecting only to put particular ones in, and then the others will fall back to a software library. Development extensions. This is the RISC-V standard indicating that these are things thought to be good. They weren't quite ready in time for this level of the profile, but they're expected to be mandatory next time. So if you're making a part, it's a good idea to put these in because they're going to become mandatory. So if you've got them in, then you won't have to scramble to put them in for the next profile. And then there are optional ones, which sort of sounds contradictory because we were saying it's supposed to give certainty to the software. These are mostly done in fairly clever ways so that you can either detect whether they're there or not very easily in a library, or, for example, the control flow integrity ones, the landing pads and shadow stacks, they're coded in such a way that if a processor does not support them, they'll become no-op instructions, or something that's in the mandatory set called a maybe-op instruction, which just loads 0 into a register. So those can be safely used by software, even though they're optional. On a processor that supports control flow integrity, they'll strengthen the checks on jumping to subroutines and returning from subroutines, and make sure you're not getting suffering from any stack overflow attacks or anything of that nature. But on a processor that doesn't support them as an optional extension, they'll just be no ops, and they'll pass through without any concern. So there is some care done with the optional set of instructions. The server specification then builds on RBA 23. You'll see that specifies the applications and the interface into the operating system hypervisor. But below that, there's a whole bunch of other stuff that goes into a server. There's how you talk to the management control. There's how you talk to the I/O system. And so the server platform spec is built on the server SoC spec, on the software boot and runtime services. That tells you how your boot software passes information up to the operating system. It's built on the security model that the RISC-V security teams put out, and generally pulls together a bunch of industry standards and says this is how RISC-V is going to support these. In particular, as I said, the Scaleway guys were really pushing the UAFI and ACPI as the mechanism for the booting and passing information from the boot code to the operating system. The server SoC specification talks about what, there's a timer defined in the standard spec, but it doesn't define what frequency it counts at. So that's tightened up in the server spec so that if your operating system is expecting a clock, it will always know what speed it's going at. Similarly, in the PCIe subsystem, PCIe is great because you can discover what's out there. The question is, how do you know where in memory you look to start discovering things? So there's a bunch of specification that says how you pass to the operating system where to look for the PCI configuration space and so on. So this achieved its goal, and Rivos and Canonical recently announced that we were bringing Ubuntu for data centers to RISC-V, and it's not just enabled for Rivos, it's enabled for anyone who uses the RBA 23 profile and the server platform specification. What this means is that Canonical can do one Ubuntu distribution and it will install across all vendors' machines, which is exactly how things work in the traditional x86 ecosystem. And there's a nice video our software lead and the canonical lead discussing that if you're looking on our YouTube channel, I would recommend the 6-minute version because it's much more complete. How's Rivos building this? Well, we're taking those two specifications. We're using them to build our CPU implementation and our SoC, and therefore we're going to be ready to work in a RISC-V server along with our AI accelerator, because everyone does AI these days, and put the whole system together. But as I said, Canonical can support us because we use the server spec and the RVA23 profile. Finally, visit us at our booth. We've got a booth downstairs in the RISC-V area, and you can visit us again at the A-Speed booth, where we have we used their BMC chip and built a Open Compute compliant DCSCM card. So stop by and see that as well. Thank you.
Thank you so much, Mr. Mark Hayter. Now, coming up next, let's welcome Mr. Liang, founder and CEO of DeepComputing, to come on this stage. And his presentation is Revolutionizing AI Computing with World's First RISC-V 50 TOPS AI PC. Please welcome Mr. Liang.
Hi everybody. Tired of the technical things, ready to talk about the real thing, get into the mass market. So, you know, and RISC-V produce a lot of things, but not really consume. And now I'm trying to get you guys to consume. Otherwise, no point stay here, right? So, and then you can see the whole COMPUTEX is all about AI. Literally, it's a media show, you know, upstream, downstream, supplier, and customers, ODM. So you will see RISC-V is pretty weak in that way. So we probably the only guy should get actually the application processor all the way to the mass market. I'm the only one guy. No Lenovo, no HP, no Dell, no Azure, no Acer, no. Okay, and I'm lucky enough to get enough support from the Intel's ODM, for tier 3, tier 2 to support me to make the laptop. So today we talk about some AI. So myself is Liang, founded DeepComputing during the COVID. So. And it always says that it's NAS CTO's fault. Mark Hume always say, "Oh, T has coming up with test chip. What to do with it?" Okay, so that started me making a software guy, making a laptop when I was in COVID in Shenzhen. So and now I set up the goal is that we need to get things into mass market. So we are the pioneer, consumer electronics. So and I make a tab and speaker. I make most of them. I know all the problems. If you got an SoC, you want to get to the mass market, before you design an SoC, you come and talk to me. I will tell you all the problems. Don't stay in the kitchen and cooking stuff, and actually I can't even use, or very difficult to use. And then I make the modern personal computing device, basically AI PC. So it's the first rumor we sold it in $5,000. So but I still lost a lot of money. So. And yeah, it's stressed enough, very stressed. RISC-V is, I'm 50 now, so in the past 40 years, over 50 years, I think RISC-V is the hardest thing everybody do, man. I earn all my money from the software and lose them all in the hardware. Okay, so I decided to invest some fun thing. I invest some toys company and runs RISC-V. So next time everyone want a souvenir or whatever sponsor and talk to me. I will donate all this. So we talk about AI, and then DeepSeek and ChatGPT is head-to-head, one open source, one closed source. I would say that I stay on the open side as a humanity personality. If we don't open, we can't compromise, we can't talk, and the only thing we do is fight and war and war and war again, right? So, And now where we are now, I'm sure that now we get into the local device with 50 TOPS AI now on the 12 nanometer. It's not too bad. It's hot, but it's not too bad. We can do a lot of inferencing and training as well, very small model, okay. So, and in the local device, we literally can run, for example, on our laptop, and this version, 7B, we can run really around 15 tokens per second. So a lot of things for my kids to understand all the mathematics and all these things, you can do a lot of things now. And also, when you connect to the network, go with Olama or Lama's CPP, you can do a front full bug of multiple machine. You can run full bug of DeepSeek. So it's good fun. Play around it with a local device, and you know all the problem, especially in the RISC-V community. And then you can feedback to Roger saying, come on, do better AIP. And go to Rivos, come on, man, do better. All right, so, and you have to play with it. Okay, now COMPUTEX, now we are, NVIDIA saying that now we don't need to run Windows, we don't need to run Linux, I'm not sure, right? So, but that here we go. So, and I would say that the RISC-V AI is good. You have a matrix extension, you have a lot of customized extension, you can run on the coprocessor. Just now, and this morning, people saying 28 nanometer can beat 2 nanometer. Feel free to do a coprocessor, and don't just do IP, right? And use a chiplet to packaging it, and talk to Tenstorrent chiplet, then you get better thing. There's the flexibility of a RISC-V. And AI PC, I started trying to get the OS running first before we can actually run. It's difficult. And I talked to, when I find it out, none of our SoC can run on the latest kernels. People can't play with it. All running on the legacy kernels. Right? And the first chip I built, a laptop went on 5.5 kernel. Can you believe that? Right? Because the IP guy tied to that kernel, and then the SoC tied to that kernel. But now we're on 70 probably, 7.1 kernel probably last year. So all are old. Then I start talking to coincident, and they are coming to Hong Kong and talk to them, and we have a meal and a drink. I say, you guys, the SoC guy in RISC-V is just out of their mind. They wait for the chip out before the upstream kernel. And then upstream kernel process take probably 9 months because politics, bureaucracy. So, and your chip is completely, the kernel use is completely out of date by the time you reach the mass market. Don't bother do it, okay? When you do an IP, start in the FPGA load verification, go and upstream your damn kernel. Once the chip out, 9 months, 6 months later, then you have an up-to-date upstream kernel, and people can play with it. And the most important thing is Canonical, Ubuntu, or Red Hat, Fedora, Arch, and all these tokens can put their distribution on it, and everybody can play with it. So Greg is send me a video, say, Yuning, go and talk to all the RISC-V guys. Gonna watch the video from Greg KH about when you should upstream kernels. Okay, and then after I found out the kernel problem, and next problem, the distribution. Ubuntu, I didn't remember when I did the first laptop, Ubuntu asking, you need to give me $1 million and wait for me 9 months and give you Ubuntu versions. I say, come on, where I got $1 million? Probably Rivos has, Tenstorrent has. I don't, right? So, and I'm lucky enough because Ubuntu is run by Mark. Mark is a historic, very strong-minded, and I just convince him saying that you are an open guy, right? You should support RISC-V. Forget about or forget about Qualcomm. Okay, we do better than you do. So even though our chairman is Qualcomm, okay. But, and they really, now they charge me nothing, they give me, even now I give them some money per device, and because I want them to help me to sell, right? They say, no, I'm not taking money from you. So they're great support, but they only support anything above RVA 3 now. So RVA20, before RVA23 is considerably dead. So for example, the chip done before RVA23, you probably can use a vertical segment, not the general platform. And from 2604, and I assuming if I sorted out the GPU and all the for all the deep computing device, the Ubuntu will build the image for us instead of we building ourselves. So of course, after we got Ubuntu, then we got another hoop, which is Red Hat and Fedora. So yeah, and NASA summit, and then I managed to convince Red Hat and Fedora give some commitment. So they will do RVA23 once we get the software, the hardware server in their build, then they should be able to support. They say it's 47 version, depends on the hardware server. So hardware server is very important. The build server is very important. You don't need to build 100% perfect. Give some server can run builds. So, and your recent announcement with Sci-Fi and Red Hat should be doing RVA23 as well, very soon, 10 onward. So sorted out the OS. What else, right? Mark just like, oh man, applications. So what AI applications? And yeah, audio, video, and definitely is one of them, right? So, and I think RISC is get a very strong support on the video codec stuff. And the web applications, so we don't even have a browser, you know? We don't even have a browser. Build, default, support, RISC-V. I'm here, and let Google to hear my voice, okay? Again, it's not the first time. And we'll continue to do it until they support us. So, and then the second thing is the same. All the IDE, I think the latest version support RISC-V and especially VS Code, but probably not Eclipse and all those embedded IDE is not. And also, we want to play some games, right? So good luck, we have a monopoly GPU. So, and that needs to be sorted out. That's why RISC, and you need to hammer on the imagination, saying that how they support on that. If they don't support, kick them out, right? So even if they give you money, right? Otherwise, so far, the upstreaming, all because GPU, right? Once the GPU not support open source upstreaming, if you have their IP, you don't even get the display out. So if for any one choice, I would say they choose a discrete GPU. If you have any problem, talk to me, okay? So we will switch all devices to discrete GPU so that upstream goes smoothly, so that Ubuntu, Red Hat, Fedora can build their image for mass productions. So, and then the rest of thing is the local AI compute. So we might have some, now AI is everything on the web. So local device might run web services. And then, and there's a lot of API you can build along the browser. So you just like web GPU, TensorFlow.js, and all people can do a lot of invention around the web, especially in browser. So the challenge of RISC-V I see for myself, right? I talked to all the SOC guys, and they don't know where the market is going. So the head-to-head with a competitor, they're very difficult. No scale economy, and they're too expensive, right? And because no market, I don't know how much power we have, right? What nanometer we go in? Very surprised me today, this morning, people saying, and we can do 28 nanometer, better than 2 meter. I'm definitely look forward to that kind of crazy ideas that we can leverage on RISC-V. Because 28 nanometer, usually a quarter or $500,000, you can do a tape out. So you can prove you can better than Tenstorrent hard work on AI. I'm sure Jim will be over the moon, straight away buy you over, right? And the second time, the whole RISC-V resource, and it's very bad. It's very limited resources and not enough resources. The whole RISC-V ecosystem, as I say, even beating ARM alone as a company. And the third time is we don't have time. My cell is around 4 years. I produce 3 laptops, never get scaled up to just past 1,000 mark, not up to 10,000 mark. You know, and there's a lot of effort. And then Rogers probably the longest. Right, so he earned a lot of money from Intel, spend them all right? So we run out of time. AI is very hard, from transformer to recent DeepSeek, and people asking for CUDA compatible and PyTorch, and then the whole thing, all the RISC-V ecosystem supporting optimizing. So porting, including the kernels, drivers. So you start with the old IP and then IP kernel, so all the way SoC you Tang, then if your SoC life is 7 years, you update it, keep porting your kernel, right? And then I think Frank knows the Chih chips, so painful, right? 6.1 kernel trying to move up to 6.14 is difficult. And then the second thing is the AI toolchain and framework is porting, writing kernel porting, right? Because everything changes. Right? When the kernel distro changes, toolchain changes, all the Go, Rust, and everything come with it. Python all changes. So porting all days. So, and I say is that I'll quickly go over is application, hardware, security. It says that if we don't break this deadlock, and it's very difficult. And I would say that the let go approach is good for that. You know, chiplet. You know, I think Tenstorrent doesn't go in the right approach. Chiplet CPU, chiplet GPU, chiplet AI, and then people like me, I can afford the packaging. I can packaging them all together becomes SoC, right? Even me can afford it. Bigger packaging is around $250,000 only. Right, and then the whole IP, SoC, product, and the Go device. To the device side, and PCIe standard, Type C standard. So use them more, right? Don't use a proprietary bus. And then even the end product, you take a look our modular laptop. We partner with the world famous startup in Silicon Valley. We can upgrade the motherboard, every 6 months. Buy a laptop, all right? Don't ever throw away the cases, throw away the motherboard. You can throw x86 away, you can throw ARM away, change it to RISC-V. How good is that? No more excuses not using RISC-V, okay? Otherwise, you never know the problem, you never fix the problem. Okay, so, and that's modular. So let's take a look that's the example. That's an example of chiplet, the first RISC-V chiplet. We have a lot of problems because the bus is not UCIe, right? And then they do very clever. It support PCIe host and device. I can do a lot of crazy things. AI card like this, and you can be host, you can be device, and can do a lot of invention around this. And I can even run the internet over the PCIe. There are a lot of inventions. So the biggest for me is that the product goes to retrofit, let go. I can focus to make a motherboard because that's enough for me to do. I don't want to do a whole chassis. I want the chassis like this laptop enough for 10 years. You don't basically enough for one whole generation. So this is a power partnership with Framework. And you can see now they push it to very literally every form factor, 12, 13 inch, 16 inch, and desktop as well. So it's for me it's good. I only focus on big motherboard. They focus on the channel, focus on the building communities. And the best thing is that the motherboard can fit onto 13 inch, 14 inch. But not for 12. So it's very affordable now. It's only $300 so people can pay and know the problem. I suggest RISC-V people should really buy one and know the problem. Otherwise, you on the paper only. And now, that's what we're going to build when whoever gives me a very powerful AI chip, you can see, this is their AMD portal, right? So you can connect them all about DeepSeek 700B. So I wish we can do it probably this year or last year, and with RISC-V. So that's what I'm planning to do once I get the chip out. So, and the other thing, as the 16 inch, this is really good invention. We have the motherboard for x86. I can have a RISC-V AI extension. So once a Tenstorrent gives me a chip, I can put it into this board. And then a PCIe board connect to the x86, and people can still do work and do fun on AI, on RISC-V. And that's the price point I will look at it. So, and hopefully we really do something great. And this is my, we need to get the 60 core out build machine, hopefully. Lucky we'll get some proto out. Supposed to be Q1, probably now they ship it because the buggy thing, they probably ship it to Q4. So we see some 64 core proto build machine now. But it's not going to be great server, but enable the distro to build some RISC-V natively. And now this is the 8-core AI PC we've done on here, and come down to our booth to taste it and see how hot is it. I might do a tablet or 4-core with LLM support, a 7B model special for kids. And the rest of the thing is 16 core. Come in. That's all for me. And if you guys want to understand mass market problem, come and talk to me. I know most of things. And we can tell you all the know-how and don't go around chasing the tail. Thank you.
Thank you so much, Mr. Liang, for your inspiring and fun presentation. All right, so follow up, let's welcome Nathan Ma, AVP of Marketing and Strategy, Nuclei System Technology, to share with us on RISC-V accelerating the future of AI and automotive computing. Please welcome Mr. Ma.
Good afternoon, ladies and gentlemen. My name is Nathan Ma from Nuclei System Technology. I'm very happy, excited, and honored to be here today. So it is actually our very first appearance here at Taipei, so I'm going to introduce Nuclei really quick. So founded in 2018, Nuclei is a professional RISC-V IP provider. We have pretty much covered all the application areas right now. Our headquarters in Shanghai, we have worldwide business and support. And we are very proud to say that within 7 years, we have already more than 300 official customers with more than 100 million shipments. So quickly go over our product portfolio. We have a general product line categorized by 4 different classes. The 32-bit embedded, 32-bit application, 64-bit embedded, and a 64-bit application. And we have 6 different series from 100 all the way to 1000. So 1000 is our currently highest performance core. It is out-of-order execution, 12-stage pipeline. And we also have vertical product lines. So NS stands for security, NA stands for automotive, and I stands for intelligence for AI. And then today I'm going to focus a little bit more on the AI and automotive. So yeah, so a lot of speakers have already spoken about the advantages of RISC-V, so I'm not going to go through the detail. But the open standard, scalability, efficient design, rapid growth, ecosystem all actually help RISC-V make RISC-V very ideal for the emerging fields like AI, security, and automotive. And then a lot of people ask me, like, how can CPU or RISC-V CPU help AI SoCs? Well, I believe besides the development, control, debug, security, etc., the parallel computing or the vector parallel computing capability of CPU can actually help to efficiently process those data or algorithms that the NPUs or other AI accelerators cannot do very well. This is very important, especially in the field of edge AI computing. We know that in the edge computing, the device must maintain or keep a balance between computing power and the computing capability, performance, and the power consumption. And by leveraging RISC-V, the AI chips can actually deliver very powerful computing capability as well as maintaining a good power consumption. So this is our software stack. So Nuclei actually offers a very comprehensive AI software stack. So in the middle is our Nuclei AI SDK. So it is adapted to different inference frameworks and provides libraries for DSP, AI, and neural network. So this enables our user to easily leverage RISC-V P extension, V extension, and of course in the future AME, IME extension. And then it's very easy for them to use. And on top of the AI SDK, we have this Nuclei AI model. This model includes commonly used AI inference models categorized to different types. And then each model is accompanied by corresponding inference code for easy integration and deployment. And our Nuclei AI model and Nuclei AI SDK can be perfectly deployed on our hardware platform, including our general processors, including our N900 and our NACC, which is a lightweight NPU processor. So this is a basic overview of our N900. So it can be configured into any RV32 or RV64 processor, and also supports RVV 1.0. It's very flexible, easily configured. Each core can be configured with the VPU independently. Now this is some highlights of the features. The N900 supports RVV 1.0 with the VLANs to be 512-bit or 1024-bit. So maximally it can execute 4 instructions, 2 scalar, 2 vector. It supports custom instruction interface, which we call NICE here in ICE. And then right now we support both scalar and vector custom instructions. So this is pretty much a high-level diagram of the whole solution. So on the left-hand side is our scalar unit, scalar execution unit. On the right-hand side is our vector execution unit. And in the middle is the scalar or vector customization extension. So this extension can be deeply coupled with our scalar execution unit and the vector execution unit, so that the memory resources are shared perfectly throughout the whole system. We do offer a highly adaptive and flexible software ecosystem. Other than the embedded SDK, Linux SDK, different libraries, I do want to highlight our nice vNice custom instruction generation tool on the top left. So we have this Nuclei model and Nuclei wizard to actually help our customer to simulate, verify, and generate instructions automatically. So this is very easy to use right now. Customer can do a lot of performance enhancement using our custom instruction generation tool. Just share some of the custom cases. We have customers in the data center video acceleration, in the CIM computing memory, AI storage. A lot of customers are already under mass production using our N900. And then this is some of those performance enhancements using 1024-bit vector on FFT, GEM, convolution, and FIR. Some optimization on the neural network, and then some the optimization on math and Onyx library. Now this is the first part of my presentation about AI, and the next I'm going to go through some progress and our experience in the automotive. So we believe that the RISC-V right now is reshaping the automotive industry, which requires flexible, open, and efficient computing. It's not just our thought. The global big names, big companies, if people join the summit in Europe, we see like Infineon, or in Japan, Denso, a lot of the big companies, they're actually, including Renaissance, they are all actively investing and expanding in RISC-V related work. Now, we actually have this NA900, which is the first RISC-V CPU IP to achieve the ISO 26262 ASIL-D product certificate. It actually took us about 2 years to actually get this certificate. So we started our automotive project in 2023. And then currently in the industry, most of the users, chip designers or OEMs, they require either ASIL-B or ASIL-D for functional safety. And then the major big difference between ASIL-B and ASIL-D is the dual-core lock step. That's why we actually provide this functional safety scheme. This is our dual-core lock step scheme. We have a master core and a shadow core running together to make sure there's no mistake in our mate. And then if the customer does not want a dual-core lock step scheme, they want an ASIL-B, and then this can actually be configured into a split mode. So 2 core can run together separately, actually. So it becomes a dual-core system. And then we also provide STL available for the ASIL-B. In conclusion, we have this NA series designed to meet a lot of different wide range of applications. So we provide the NA ASIL-D series, we provide the NA ASIL-B series, as well as our self-designed STL. We actually have a lot of customers right now. We're doing pretty great in automotive industry. Currently, we have customer in LiDAR, I think the millimeter wave radar field control, high performance MCU, Ethernet gateway, GNSS, and SoC safety island. So currently we have more than 18 NA licensed customers, of which 5 of them are already under mass production. And then 3 of them have ISO 26262 certification already. This is one of the example. This is actually, Sylogis happened to be an IPO company here in Taiwan. So they actually, they used our NA900, and then it's already under mass production. This is some of the information of this collaboration. So they use 6 NA900 cores. support dual core lockstep and split. I think 2 of them are fixed to be dual core lockstep, so you have maximally 5 core computing capability. This is our NA900 diagram. I'll just skip it. You can find it online on our website. So the NA ecosystem landscape. So we already have a lot of ecosystem partners from Safety, RTOS, AutoSAR, IDE, compiler, and debugger. And then this number is continually growing. So this is my final slide. So this is our thought on the future outlook of the RISC-V automotive CPU IP. So we've put a diagram here. On the x-axis stands for the ecosystem dependency, and the y-axis is for performance. So we can see that RISC-V has already successfully addressed in a lot of areas like the LiDAR, like chassis control, battery management, body control, etc. But we still see there's a long way to go in the intelligence cockpit and the ADAS SoC control. So for the intelligence cockpit, the support for Android, for the QNX, we do need that support. And then for the ADAS SoC controller, again, the software ecosystem and the customer confidence is also very important. So nevertheless, we are still looking forward to seeing RISC-V success in those 2 areas under the effort of the global community. Okay, so that's all for my presentation. Thank you. And
Thank
enjoy
you
the
so
rest
much,
of the day.
Nathan. Now, please join me in welcoming our next distinguished speaker, Mr. Ming-Yang Chih, founder and CEO of Chelpis Quantum Corporation, and share with us at the topic of autonomy robotic system architecture for the quantum era, building AI plus PQC, secure robotics with RISC-V architecture. Please welcome Mr. Chih.
Thank you very much. My name is Ming Chih, the founder of Chelpis. So today my topic is why different compared with our original topic is encryptions. So we are building a robotic now with some of partners in Taiwan. So let's go to first page. So for our world, we need using AI every day. For example, this generated by AI. So the world will be modeled by robotic AI systems. So 2 days ago, Jensen Wang, he says, okay, AI factory will be the trend to next years. A lot of factory will start to adopt the robot. But how they do it, and what kind of a robot can fit into the AI factory. So let me introduce latest. So the robot visions that power tomorrow, from my point of view, at least you need to let your robot can more understand physical world, what it is. So sensor is very important. And second one, you need kind of open platform on the robot, because robot is very complicated, cover different kind of area, from mechanical, from the motor design and the battery. So this robot also needs a way to very easily to adopt exist workflow in the world. So that's my visions. And because the robot compare with all the notebook and the mobile phone, it can work and operate some things can damage the world. So everything we need to consider about the cybersecurity, especially on the post-quantum cryptography. So here's our vision. So robot to anything. One thing, AI robot need to working direct with a human, not only devices. And the second thing, you need to control and very, very carefully for every pace when you pass your tokens or control message. So this kind of device definitely need a AI large language model. In the fab, we now is kind of a hybrid structures, 5 robots, 2 people to working together to solve every things in the product lines. So what kind of encryption we will adopt into the infrastructures is a PQC. So algorithms evolve every day because of computing power goes up rapidly. So in the first quarter, you can see the NASDAQ, all the computing quantum computing company, their revenue goes 500 times compared with last quarters. So which means a quantum computer is become very, very mature. So this picture shows all algorithm we're using will year by year, their security level will be decreased to very, very low. It cannot be used. So some of algorithm we are using need to change soon. So quantum computers can break in some algorithms in a minute, but using the traditional computing power, you need a larger amount of years. So we need to fix it. So we adopt and join the global standard with a NIST to invent post-quantum cryptography. So NIST finalize a few algorithms last years. Those algorithms, we are already implement some of the solution on the RISC-V platforms with not only hardware circuit, but also some extension instruction set. Yep. So the vision we see in a, for example, a use case in the fab is the chips, their spec need adopt the AI with the LLM, and then it can direct to support the encryptions, because all the critical path is very, very important. And from robot to robot, robot to humans, every communication should be protected. So here's some key parts for if you want to build in a drone, robotic, and robotic dog. Here I have some common parts on those devices. So you can also see for a robot, you need to find a place to put your battery, put your motors, and let your controller become smaller. So we have a project start from this year's to building a next generation RISC-V chips with those features. That chip can widely control many different the end parts in the robot. So not only this chip, we also building some software systems how to protect data, how to protect the authentication life cycle, and help our customers can let the drone or their robotic can go into a field to adapt their environment with security. And we also have some learning framework structures that our chip can keep learning how to optimize when they go into a new field. So Chelpis is going to building a group or cybersecurity ecosystems with many different kind of partners with the sensors and the motor controllers and some cloud system providers and of course and this to building a new systems for robotics. So here is our infrastructures. Chelpis work for open source area for very, very long times. So if you're using any kind of PQC library, that comes from our company. For example, if you're using the Signal, the PQC algorithm is developed by our teams. And we also join many different alliances. So that's the two page. We are going to announce our development open platforms on the robotic drone and the robotic dog. So if you are this kind of area customers, you want to build in your robot, you want to build in your drone with partners, have an open platform, welcome to find us. So keep follow us, building your drone and robot. Thank you very much.
Thank you so much, Mr. Chih. Now, up next, please join me in welcoming our last speaker for today's program in the stage. Ladies and gentlemen, Mr. Roger Espasa, founder of CEO of Semidynamics. His topic is enabling NPU AI compute entirely on RISC-V ISA.
Hello, and thank you for the invitation. A pleasure being here talking to you. And today I'm going to talk about our recent announcement, an NPU completely built using RISC-V instructions. And I'll discuss why you care and why you want to use this type of NPU instead of buying the other ones you can buy on the market. And the name, if you know how to pronounce a very famous American company, Marvell, you know how to pronounce this. It's called Servell, so it's the same thing. It means brain in my native language, right? So that's okay. So let's go. Why would we do an NPU based on RISC-V ISA? You're all thinking, oh, come on, there's a lot of NPU vendors. I don't need one more. Why should I be listening? And the answer is that AI models are changing very fast. So not even NVIDIA, who owns the whole show, knows what's going to happen in 3 years. They have no idea because somebody somewhere in the planet is going to invent a new type of AI model, and we'll all be struggling trying to run that AI model, right? And so what you need is a ISA, you need a solution that is completely flexible and that is ready that when you're shipping your silicon 2 years from now and somebody invents something new, your silicon is still good. You don't have to throw away your silicon and many millions of dollars of development, right? And we think that the vector instructions and the matrix instructions in RISC-V are more than sufficient to create such a, oh, I have a screen here, sorry, such an NPU, right? So, and the software support, I'll talk a lot about it. Once you move to RISC-V, then the software support becomes a lot easier. All these other NPU companies, they're all trapped in the problem of how good is your compiler? Right? Oh, there's a new model. Can your compiler run it? Oh, sorry, yeah, let us work for 5 months and we'll come back to you. You know, the compiler stack is very complicated. And so we need something simpler that a model comes out and in 3 days you have it running. Right? That's what we need. So this is what we created, this NPU called Servell. It can go all the way to 256 stops in 4 at 2 gigahertz. We can run it lower frequency. For those of you that don't like high frequency, no problem. That's no problem. And of course, it runs the old stuff, but it runs the new stuff too. It runs LLMs and it runs anything on generative AI, right? And all of it is AI. And we'll talk about the details in a second, right? So how did we do this? What is different from the other NPUs? And I'll have a diagram describing how it's different, right? So we started with our CPU, which is a RISC-V CPU, out of order, very nice CPU. And what we did is couple very closely a vector unit. Some of you will say, well, no surprise here, we understand that. But then we coupled very closely the tensor unit. The tensor unit does fundamentally matrix multiply. So tensor multiply, tensor vector multiply, whatever you name it, right? We support all the data types that you see here, and we added a key secret ingredient, which is called the gazillion unit, which is the thing that really brings data from the memory to the tensor unit. Because running these AI models has 2 problems. One is doing matrix multiply really fast. That a lot of people can do. The second problem is bringing the data from the memory into the matrix multiply. And caches don't help because these models have 14 gigabytes, 20 gigabytes, 30 gigabytes, right? So, you know, this slide illustrates a little bit what I was talking about. On the left, you have the old style AI architecture, which many of you are talking about, right? You have some cores, you have an NPU, which you'll go buy from someone. And what is the problem with that yellow NPU? Well, first, it's secret. You go to an NPU vendor and it's going to say, oh yeah, it's fantastic, it's much better than the one from Semidynamics, but he's not going to tell you how it works. He's going to give you a horrible manual and you won't know how to program it, right? And on top of that, you'll probably need a GPU from a vendor that was mentioned before. So the long list of problems is that these things, the way people build them, need DMA copies from yellow to blue, from blue to green, from green to yellow, right? You need to move data from these things. This is complicated and difficult for software. You need 3 software stacks. You buy the yellow from one vendor, you buy the CPU from another vendor, and what do you get? 2 software stacks. And now you have to combine the 2 software stacks, and that's a problem for your chip company that's doing this, right? High latency, non-optimal PPA. Instead, if you take our approach, everything together, no DMA. You're programming a RISC-V program. There's no DMAs anywhere. You're just doing loads and stores, which all of you that are listening here know how to do, right? It's a single software stack. Guess what? It's called RISC-V. So you're not inventing anything. You know you can use the tools. You can use any of the tools. Today we've heard a lot of great tools that are being developed. All of those work here, right? Well, you get a single hardware vendor, which makes me happy, but also makes you happy because you don't have to deal with three people, right? And zero latency. These 3 things are exactly at 0 cycle distance, right? You don't send messages from one to the other. The registers are all visible, so that's really good. And that gives better PPA, balanced scaling, and is future-proof. And this point, many people ask me, well, you say it's future-proof, but that's just a marketing slide, right? You don't know. No, I know it's future-proof. How do I know? Because this thing is under control of a program. So whatever this person that we don't know invents in 3 years, you can express that model into a program. So we know it is future-proof, right? So it's very different from old NPUs, the ones on the left, right? So what can you get? I mean, the way we've organized this is the building block, but then these building blocks get replicated, and we can ship you, since it's called Cervell, we call it the C8, the C16, the C32, and the C64, and these are the performance we can give you at different data points. And if you need something else, just talk to us. We're more than happy to customize for you, right? And you can see that you support for activations and convolutions. We can support any data type you want. Software, super important, right? We have, because it's RISC-V, the beautiful thing is that I could skip this slide. I'm not going to do it, but I could skip it because compilers, GCC and LLVM, emulators, QEMU, there's nothing special here. And that should be good news to you because you don't have to rely on me to get that software, right? So if you don't like my software or my packaging of the software, don't worry. You go to RISE and get another one. It doesn't matter, right? The key beauty of RISC-V is that you can write your own software, right? We do provide, and I want to talk about it, this AKL. Some of you may know from Intel MKL, so the name will sound familiar, which does contain a bunch of pre-cooked algorithms. Obviously, we have an optimized matrix multiply, FFT, convolution, you name it, right? So we do have that library. If you don't want to write it, don't worry, we will give it to you. But if you don't like ours, we always say the same. If you don't like our algorithm, you can code it yourself because there are no secrets. It's all RISC-V. You can code it yourself, right? And then let's get to AI, because this is an AI NPU, so I should say something about AI. What we decided was to focus on ONNX. We do realize PyTorch is a little bit more famous, but ONNX is actually a lot simpler and much easier to get running on anything, and in particular on RISC-V. So as you know, ONNX is 2 things. ONNX is a file format, so that's uninteresting, but there's also something called the ONNX runtime, which is a program created by Microsoft, which you can download. It's open source. It's under the Linux Software Foundation. And the ONNX runtime can take any ONNX file and run it on your hardware. And that's exactly what we did. We took the ONNX runtime, we ported it to our solution, and we pretty much can run any model, right? And to prove that, I asked my engineers, okay, we go into these meetings and we tell people that our solution is super easy to program. We tell people that it's trivial, anyone can do it. Okay, DeepSeek is out. Show me that we can really port DeepSeek in a few days. let's see if what we say in meetings is really true or not. And can we run DeepSeek was the question I asked them, right? And they said, sure, this was released on January 20. This is not our slide. This is from the DeepSeek people. You know this. And you know, you have a model in PyTorch, so you can go download the model yourselves. And once you've downloaded the model, what do you have to do, right? You run something called the PyTorch.ONNX converter. Pretty much all AI practitioners know how to do this. I don't, but you guys probably do. Then you create what's called a runner. A runner is a little program of, I don't know, 20, 30 lines, which reads in the ONNX file and runs it. And then you connect it to the ONNX execution provider. And what do you get? Well, you get here, you cannot read from the back, but it say, hey, user, what is 1 + 1? And here DeepSeek is thinking a lot and says 1 + 1 is 2. So really impressive, but the thing is, this was done in what, three days of coding, 4, and the problems were more about downloading the DeepSeek model, getting the right weights, and problems like that. Nothing to do with RISC-V or nothing. So our solution is really easy to program. The software is ready, the AI is ready, and even if you don't like our software, I love to say that many times in my presentations, you can write the code yourself because you're going to get an NPU that's all RISC-V, and you can just program it any way you want. You can invent the next AI in the world. So of course we can run DeepSeek. And we obviously run a lot more things. So here's a quick snapshot of the things we run and many more, right? So no problem. Tell us what you need and we'll get it for you. And with that, thank you very much for having me here.
Muchas gracias, Roger. Thank you very much. Now, ladies and gentlemen, we're now kicking off today's highlight session. This is going to be our last stage. So our panel discussion, please make sure to remain, and we will also have another lucky draw. So maybe it's you, and you're gonna maybe have another prize coming up. So as AI, edge computing, and also intelligence system rapidly advance, the semiconductor industry is entering a new era of architectural innovation. Now, at the forefront is RISC-V, an open instruction set architecture that enables unprecedented flexibility and customization. Now, gaining a strong momentum across industry and academia. In this session, we will also hear from leading experts across RISC-V ecosystem as they share insights on how RISC-V is driving the future of AI. Now, from chip design and system integration to security and also ecosystem collaboration. All right, so let me first introduce our moderator of today, Dr. Jeffrey Cho, CEO of Ansforce Incorporate. He's also a creator of a popular YouTube series, Technology Introduction and also Industry Application. Now, please welcome Dr. Jeffrey. Perfect. Now, our first panelist is Mr. Frankwell Lin, the chairman of RISC-V Taiwan Alliance. He is also the chairman of CEO of Endes Technology, where as a co-founder, he has led the company to become a global leader in embedded CPU IP. Welcome, Mr. Frankwell.
Thank you.
Now, next panelist, we will have Mr. Luba, the board chair of RISC-V International. He is also the senior director of technical standards at Qualcomm, where he leads the company's semiconductor standard strategy and industry management. He has previously led Qualcomm SoC design and flagship products like Snapdragon 8 series. Welcome, Mr. Luba. Now we also have another panelist, Dr. Charlie Su, the president and CTO of Endes Technology. He is the company's first employee, and Dr. Su has been instrumental in building Endes Professor IP businesses from the ground up. Welcome, Mr. Charlie Su. Next panelist, we have Dr. Liang, the fellow of Tenstorrent, specializing in RISC-V CPU and machine learning architecture. At Tenstorrent, he leads the team focused on performing modeling, workload analysis, and also optimizing the high-performance RISC-V CPUs. Welcome, Dr. Luke. Now, last but not least, our next panelist is Mr. William Wei, CMO and also EVP of Skymizer. William has named us the top global 100 leaders in technology in 2021. He previously served as CTO of Foxconn Group, where he leads the technology strategy of EV, robotics, and digital health. Please welcome Mr. William, and now I will pass the stage to Dr. Jeffrey. The floor is all yours.
Thank you. Welcome everyone to join today's discussion. So we all know that RISC-V is an open source instruction set for all the industry. So the first topic we would like to talk about would be the core advantages of RISC-V. Why RISC-V is better than other solutions. So Frankwell, probably you can go first. Give us some comment.
Thank you. I've been serving as a board director in RVI and also the chair of RISC-V Taiwan Alliance. So my observation will be different from this perspective. I would say RISC-V bring a new stream to the industry because the ISA standards, Intel x86 and ARM are getting old. They have a quite much back history and some overload on their shoulder. So RISC-V is kind of young, innovative, and strong, eager to create new things. And this is the momentum generator for all of us sitting here, not only those people creating IP or chip or boards. The OEM, ODM vendors sitting here might also require RISC-V because what is the difference if you apply ARM's product, okay? There's no differentiation. You need differentiation to make your company having a new momentum to move on. So I would like to have the other academic or organizational statement of advantage to other panelists, but I would like to observe this from Taiwan's industry's point of view. From that, I would say anyone sitting here, if you are doing OEM, ODM, or a chip semiconductor, even further system board design or manufacturing, you should have this opportunity to observe what is RISC-V's advantage. Thank you.
So, Walter, would you give me a comment from RISC-V International?
Yeah, so since I'm the board chair for RISC-V International, one of my key tasks is to make sure people call RISC-V ISA open standard, not open source standard.
Oh, okay.
So there's an important distinction. Open source, quite often people think that's the whole implementation, just like the software source code. It's open source. Open standard, it's just another way to describe a standard process, just like a Ethernet standard. But similar to Ethernet and other standard, it does not charge a royalty fee. Before RISC-V, I think all the ISA, they always have, been charging people fee, at least the mainstream ISAs, right? RISC-V is so unique in the sense that it doesn't charge a royalty free. It has a free access across the world that we don't have a way to describe it. And over the time, people just kind of associate that with open source. And, we just want to remind people when you buy the RISC-V IPs, the implementations, it's not free. You still have to pay for it. However, this technology, the baseline technology, ISA, is open and accessible. And that is one major uniqueness from our philosophy, that because it's open, everybody can look at it, and not only you can look at it, you have a voice. You have a voice on how to improve it. And when that voice is available around the world, that allows the innovations.
Okay, thank you. So, Dr. Charles?
The second important feature for RISC-V after open is extensibility. So because extensibility enable a lot of creativity, allow you to kind of differentiate your processor. And it's kind of pioneering this because we are, if it's just extensibility, everyone can go there to kind of edit if you know processor. But a lot of SoC companies like to, for example, enhance their AI algorithm with some computation. But they are not CPU expert. So they really need tool to help so that they can kind of focus on the functionality they want to add. But whatever related to processor, and you can give it a tool. So that's what Andy's automated custom extension do for this. And extensibility create another some controversial. People saw extensibility would create fragmentation. But if you think about, for example, a smartphone, Android phone today, do you think the code running on MediaTek and Qualcomm, the binary are exactly the same? They are not. Because so even though in the code running on ARM processor is probably mostly the similar, but when you need to touch, for example, your peripheral devices, your hardware accelerator, CPU need to execute different type of instructions. So how do you make Android able to run? Because you create an abstraction layer, right? So above that abstraction layer, everything is the same. Below the abstraction layer, you allow vendor to differentiate. So even though custom instruction can code processor, we can still use that way to still enable creativity, but not to create fragmentation. So I think extensibility is very important just after the open standard.
Yeah, how about Luke?
Sure. So I totally agree with all the points that everybody else before me made. One thing I would like to add is also another viewpoint, which is one of the ways that Tenstorrent thinks about the problem also is not just the open standard for RISC-V, but also how do other companies sort of integrate different IPs in a sort of a scalable way, right? So that everybody can work cooperatively and still build SoCs. So that's why we think that something like the open chiplet architecture is a very valuable thing that the community should benefit from, and we're helping to drive that discussion. And once that is sort of been adopted, then in theory, any company should be able to focus on their core technologies, whether it's CPU, GPU, AI, and then have the whole ecosystem be a heterogeneous system where we can build and mix and match IPs in different chiplets. So that's a very important aspect.
Thank you. And how about you, William?
Yeah, I'm coming from actually a very different goal, different angle. I'm coming from the software industry, right? I used to work for Apple, and then we used to use 6 chip, not even RISC. So back to 30 years ago when I was in grad school, and we were studying RISC architecture. What's the benefit of RISC architecture? Simpler, right? And compiler more friendly, and more efficient, more scalable. And then now we jump into, it's a long way to go. Now it's RISC-V, right? So this open standard that provided to the community, I think is the beneficiary for the technology for a long past evolution way. It is community-based instead of a dictatorship, right? to me, it's like, oh, okay, community-based. So the more community join, although with this freedom, but the technology will last longer instead of a dictatorship, right? So I'm hoping, I'm a user of RISC-V, we use Andy's chipset for our whole system, right? So to me, I'm neutral from the technology point of view, but it just happened like, the flexibility and then the community, we use Andy's. So I hope these kind of a strong character of a distributed community base instead of dictatorship will last longer. That's my take, yeah.
Okay, thank you. Let me clarify a little bit. RISC-V is not an open source, which means actually it is an open standard, so everyone can use it. But you got to design the circuit by yourself, right? If you do not want to do that, you can purchase the IP from other companies. So that is not open source, okay? And we all know that AI is the future, very important topic in the future. So what is the advantage of customer if they use RISC-V for AI design? Could you share some core technology of your company for all of us? Yeah. So please, Frankwell.
This time we take turn from
William first.
Yeah, it's very interesting. Like, what's the relationship between AI and RISC-V? I don't find any relationship, right? But again, it's the community power to encourage to adopt this standard, and hopefully this adoption will be a long way to go in when technology innovate. Right now, we're focused on agentic, right? So agentic, you can see this keyword agentic only get popular for last 6 months, I guess. But last year, I remember last year in COMPUTEX, we have a demo. We have demo in automotive, which is where I'm also coming from. Kind of I don't know if you heard of a program called 霹雳游侠 here in Chinese, right? There's a kick. There's a supercar, right?
Supercar, yeah.
Michael's supercar, right? It called it Buddy, right? So we have the demo for agentic AI. At that time, we call it Genie, right? So now it's agentic. So you can see that's autonomous driving, but you can see in automotive has agent everywhere, a swarm of agent, right? So when you're looking from the agent, AI agent, and what's the behind agent? It's LM, right? So what's behind LM is chip, silicon. So now you come to decide, what kind of silicon you want to be based on. So in RISC-V, there's although the tool set for RISC-V, I was just talking to Luke about RISC-V right now. He was commenting about, we better have a more standard and better profiler, for example, right? But the community moved really fast. We are hoping choosing this, we can have a last longer support of this the technology path that we choose. So that's about it. Not the current, the best, but we looking for the long run. So from the top, from the AI to the why we choose the RISC, that's the reason behind it. Yeah.
So in terms of Tenstorrent's history with AI processors and RISC-V, when the company was founded, the founders were basically targeting CNNs. None of the LLMs existed, so they're using mostly RISC-V just for specialized control to basically control their custom AI accelerators. And then fast forward to today, the same, I guess, RISC-V controllers that they're using internally within the AI processors, that's still applicable. And then the only major things is obviously the precisions and the type of speeds and feeds that are necessary to actually do AI processing. So I would say RISC-V was a very good sort of a marriage between being able to control the AI processor as well as being able to scale to other different models as well relatively easily. Yeah.
How about Dr. Su?
I would say AI is now, right? So I think everyone in this room probably already using ChatGPT or DeepSeek or Copilot, right? So it's already now. And it will be more tomorrow. So I think this is a good trend. So Andy's starting in getting to AI, I think in 2019 when Meta kind of started to work with us for their first generation of MTIA. And since then, I think at that time, RISC-V vector processor just get started at point, not even finalized yet, so it's 0.7. But we continue to kind of developing the vector processor to support all the features there. And then once vector start kind of get mature, I think because AI continue to evolve, right? So a lot of algorithm will continue to kind of come in. So, and some of the operator really very important, but it's too heavy to make it become standard instruction. So extensibility here is very important. So our environment actually invented before the vector processor. Actually, we can use it to enhance the instruction. So to support something like exponential, sigmoid, all kind of nonlinear function, which is too heavy to make it standard RISC-V instruction, but very important for AI operator. So we kind of have that environment to allow our AI customers to kind of use that to speed up their custom algorithm. So I think that's very important. And as we go, I think people see we kind of moving target from the cloud AI. Now a lot of customers want to do the edge AI. And they don't have all the expertise like the other company. So I think for things like metric multiplication or NPU type of thing, which are really helpful for them. So we kind of start to implement that. And fortunately, RISC-V also, in terms of standard instruction, we also kind of want to standardize metric multiplication. And for some applications, they require very efficient application in the edge. We can implement the NPU ourselves, but that's kind of tightly coupled with our RISC-V processor because, again, software ecosystem is really important and a lot of things you need to run it on the RISC-V. So from like MLIR, from the PyTorch, TensorFlow, and so on. So I think RISC-V really create a good ecosystem no matter what kind of acceleration you use, either based on RISC-V instruction or based on NPU, but you really need a general purpose processor behind that. So I think RISC-V is very good, and AI is here.
Thank you. So how about Bochi?
Yeah, so I think RISC-V was not developed for AI. I mean, when RISC-V was invented, AI has been there for many years, but it was not as hot as these days, right? But RISC-V was developed for flexibility. And AI is a revolutionary technology. It requires some of those flexibility. And whenever you have a technology revolutions, and that kind of showcasing, gives all those new kids on the block a chance. And also, it kind of showcasing the legacy ISA's disadvantage. I think because of that, makes a RISC-V more applicable for AI. It's not that we were designed for AI, but AI fits us the best. Yeah.
Thank you. So,
okay. Last night I spent 1 hour watching YouTube with Jensen Huang's keynote speech in COMPUTEX. It was 1 hour and 40 minutes, but I used a quick turn to quickly do my view on that because some of that are the same with what he did in last year or earlier this year in the CES. But anyway, the point is, Jensen said, NVIDIA is not a GPU company now. It's not a AI company now. It is a AI infrastructure company now.
AI
so
factory.
AI is really changing everything. I would say, we as sitting here for this seminar, we come from all over the world, but from audience, you come from Taiwan as major. So what is AI really affect you? We know companies may have RISC-V chip design or IP design from our sponsors today. But from our audience, you may apply those chips or IP to your job. But we know nowadays AI changes the world. Some companies, they may have a budget change from hiring more software engineer to change to buying more AI tools and less budget for manpower. So we should think about it. But from Taiwan's industry, starting to know that there are many AI chips made by RISC-V, or systems coming with more RISC-V-based chip on it. Now is the time. There are more and more coming up. So we should try to learn this, because those AI chips, they have a innovation, they have a differentiation. Again, NVIDIA goes to be AI infrastructure, but there are many, many more categories that come with a new AI application. So we should try to learn how to leverage this kind of a situation and leverage the strengths of RISC-V, so our company could be differentiated with AI category. Yeah, that's my observation.
Well, thank you. Jason Huang's video takes 1 hour and 40 minutes, right? And every time after his speech, I will have a Chinese version. It takes only 30 minutes on YouTube. Okay, that is an easy version. Okay, we know that RISC-V start from, I remember, 2010, right? So it takes only 15 years. So the architecture, the design concept are brand new compared with x86 or ARM. So, but hackers or crackers attacked our computer system for many years. So how do RISC-V address increasing security challenges, especially it is an open standard? So Frankwell.
Okay. In terms of the level in instruction sets, that is different from so-called IP or chip design in microarchitectures. So in ISA or architecture level, there's a way to deal with that. There are specifications on hardware, or even define the ISA to deal with this kind of subjects. For example, in RVI, we have working groups defining IOPMP and so on. And then in terms of ISA, there's cryptographics and vector cryptographics, hypervisor. This kind of ISA collectively are all contributing to a microsystem security issue. So there are more and more coming up. In fact, dealing with a security issue for a microsystem is quite an issue, because users or customers, they do have needs on security, but usually they don't like to pay. Or they only pay for those that they think it is required. So as a vendor, you need to carefully evaluate the adding to the product of the system or chip or your solution. You have to think about it. Nowadays, I push our new CEO in RVI, Andrea Gallo, to that when he thinks RVI is ready to have a total solution for security, he should signal that soundly, to the world. Before that, I believe the whole RVI and the RISC-V community are preparing. I believe everyone here could tell more. I leave that to them. But I would say, from users' perspective, we encourage them to raise the requirement of security. But users should also think about how much you want to pay, all right? And from vendor you should think about how to leverage the security specifications or solutions, hardware, software ecosystems that RVI and the community already provide, so you can leverage them and prepare a solution for that.
Thank you. How about
Yeah, I think I will probably address this from two aspects. One is if you're talking about what RISC-V ISA does, what we provide is more of a security features that within our ISA, we make sure all those security features are available. So when people implement a CPU, they can implement those security capabilities to having better protection. But if you look at from the security attack perspective, quite often those attacks are on the actual implementation of the CPU. Very rarely the security attack, from the hackers is able to explore the ISA level issues. ISA, I don't think I have ever heard a security feature breach is on ISA itself, whether it's legacy ISA or the newer ISAs like RISC-V. But one major difference on RISC-V is if you look at the legacy ISA, x86, you have 2 vendors. ARM, it's 1 vendor, right? RISC-V, you have many, many IP vendors. So now if you do have a security attack, somebody will successfully explore a CPU implementation issues. With the legacy vendors, you have to wait for the vendor to fix the bug. While on the RISC-V, because you have so many vendors, you have options. That's one thing. Secondly, because you have options, the vendors are probably a lot more worried about having those bugs, and people tend to be a lot more careful to make sure those bugs do not happen.
Thank you. Dr. Su.
I agree with what Lou just mentioned. So, but but on the other hand, also agree with what Frank said earlier. I think security for most applications, they would kind of cherry pick what is needed, because most of the security feature added would incur some costs on their area, power, performance, and so on. So unless they got pressure from their end customer, which the eventual end customer probably kind of everyone, right? So if everyone raised the standard for that, the product requirement go to SoC, go to processor would have that. I think thanks to RISC-V, we have a lot of different security features there. Some of them maybe overlap. Some of them may be more sophisticated and cover more security hole, but some of them cover less. But I think it's good so that the customer can, based on their end application, to choose what is really needed to protect in their application, right? If they protect something, if their application in the security part need to protect something very valuable, and then they would increase people's hackers going to attack them. So that's why they want to protect that. So from IP perspective, we will tend to implement as many as we think reasonable. But our processes are configurable, so custom can kind of choose what it make most sense to them. So I think the combination of many features and also kind of the process implementation, we make it configurable would be kind of a pretty good choice as the kind of we continue going on in this unsafe world.
So I agree with a lot of the other points being made. In my mind, the way I think about this problem is security is a very complex and multi-layered problem. So on the software side, I think, in general, I think people will agree that if it's open source software, that's more auditable. You can go inspect it, so it's maybe safer in that respect. On the hardware side, I would say on the ISA level, there's been a lot of ISA extensions that, like Lou pointed out. For example, on the control flow integrity, there's the landing pads, shadow stacks. There's things like trusted execution environments. And then on the implementation level, that's where a lot of the attacks that you hear on the news, they come out, right? Like Spectre meltdown, any of the side channel attacks. These are all because of there's a very tight tension between very high performance implementations and speculation, right? And typically when you have high performance CPUs, you incur speculation, and then that's basically where a lot of all these attack vectors come in. And so there's this constant battle between having very high performance CPUs and having very safe implementations of those RISC-V CPUs that are passing all those known security issues. Now, having said that, there's always going to be security flaws that we haven't uncovered yet. Really, it's just a question of how quickly can you address those, and then what's the trade-off between performance and the coverage that you're speaking. So,
thank you. How about William?
Yeah, also from my angle, I agree with everybody already covered. And one thing that I want to add is when the vulnerability attack area, and also because you compare RISC-V to ARM. ARM is by one implementation, the addressable market space is much, much larger. And then for RISC-V, you have so many vendors, you have extension. Also, it's because it's an implementation issue. It's nothing to do with whether you use RISC-V or ARM. It's a multi-layer of hardware and software. So one advantage is, like I said, it's a community. So RISC-V community is really active to support each other. So I think just like open source, it's much more secure by evidence that it's going to be fixed pretty soon.
Thank you. So
excuse me, and can I add the comment? And then later on, when being asked, I can be the last one answer. I like to have two more examples. One is Cherry. RISC-V International Association is having a task force defining Cherry instruction set that is also a standard for security. Secondly, not necessarily ISA, but standard for those security organization like NIST, NIST. They have a new standard defined. So people are following that kind of a standard design PQC chip, post-quantum cryptography chip or a solution. Still, they can leverage RISC-V cores. So again, RISC-V can be used to apply, no matter you apply the instruction set or not, or simply the core to follow the national standard for security. Or you can have different perspective to prepare security solution for different kinds of security requirement.
Okay, thank you. So I think because RISC-V is open standard, so if there is any security issue, I think many people could find out and solve the problem. So it makes RISC-V more safe. Okay. So the final topic would be the application. So how should the ecosystem collaborate RISC-V on end equipment? So how about we? Do you have any comment?
Can you rephrase your question? I'm sorry.
Oh, sorry. How do customer or user implement RISC-V on end applications?
Currently, Skymizer, we don't implement RISC-V. We create our own instruction set. So I'll skip this question to.
Yeah, so I guess from my perspective, there was a lot of good talks talking about the software communities. So today, I think I like to just give the shout outs to people from RISE, right? So I think the RISE effort has been a very transformational effort in the community, because that's a way for the community to band together and then tackle some common software ecosystem issues. And I liked all the examples that was pointed out for RFQs, right? I think these are all things that the community finds very important to address on the RISC-V software ecosystem side. And I think from my personal perspective, I see a lot of progress being made probably every month on the compiler side. Compiler performance improving, especially on RISC-V vectors. And I'm sure that there's other things going on which is also very important for system performance as well. And then having standards like the RVA23 profile, as well as the different tiers, especially the platform profiles, that's super important for getting widespread adoption across the OS distributors across different hardware implementations. So all those things make a huge difference.
Okay, thank you.
I want to kind of mention RISE here. So RISE is RISC-V software ecosystem. I think that organization helped to kind of put together all the most important software ecosystem to start to kind of developing, because it has all the key player in RISC-V International, and then there we kind of everyone agree on what's the most important software ecosystem, and then we don't kind of overlap the effort. So that instead of that, if you do this, then we do something else, so that we can create a software ecosystem faster than if everyone do it by themselves. So and there, so RISE we create a lot of things. Everything will be open source. So the end customer can kind of go there to pick it up if they can to see whether they can leverage. Certainly, the fundamental development tool is there, and when they want to develop application. Like today, we have a talk by Ruinland, which is Andy's member. He runs the system library. From there, a lot of components can be there, like, for example, the audio, video codec, and so on. So if you want to do multimedia, there's a lot of things that can leverage. So I think if you want to develop software as portfolio and product, first you probably can go out to kind of check out what RISE has, and certainly welcome everyone to kind of join RISE to continue to kind of push the software ecosystem. But there are a lot of resources out there to enable the application development. So today even AOSP is there. So if you have RVA23 compliant hardware, and then you have Android, and you can start to develop the software on top of that already.
Yeah, I think this is a perfect question for this panel, because all of us are hardware people, and a software person turning into a hardware person. So we can, talk about hardware. Maybe we can talk about system software, but this question is about application software. I kind of want to relate this thing to one of the very first question on the advantage of RISC-V. I remember some of our panelists says RISC-V versus legacy. I says, you don't want a dictator. You want a community-based democracy. But I also want to add that a dictator that listens to his people might actually do a pretty good job. And if it's a community-run one, and depending on your definition of community, if your community is only a very small community, you're not including the actual application software people in there, that you may not be implementing your hardware or implementing your system software properly. So I do want to make sure that we expand our community outreach to the upper layer application software people so that we can get their feedback and get their inputs.
Yes, thank you. Frankwell?
Yeah, today I wear my hat as chair of the RISC-V Taiwan Alliance. So I like to express my opposition from this point of view. Currently, RVTA has nearly 100 members, and they are quite a wide distribution. So we have hardware company, system company, software company. So I don't quite agree with William today, because today Skymax, you come,
Skymizer.
I'm sorry, you come to sponsor this this forum because your company has a solution for RISC-V as a compiler, right?
Yeah, as a system, yes.
Right. So in that perspective, our members in RVTA, they have their different kind of perspective for RISC-V. They all contribute to different kind of application. No matter it's AI or automotive or security or MCU. Another way you observe that we can leverage my company's advantage or strengths on hardware, software. Maybe we write drivers. We contributed to some layer of chip design that can contribute to the SoC that also is a RISC-V based. So in this point of view, I still believe that in Taiwan, different layers of industry provider or industry companies, you can leverage RISC-V strengths in various kind of application. That's what my observation is.
Okay, thank you. So I think we still got 3 minutes, right? 3 to 5 minutes. So
no, only 1 minute.
Was 3 minutes ago.
Do you have any question for all the attendees? We have 3 to 5 minutes more. No? Okay. I think, yeah. So this activity probably gives you all the answers, right? So, yeah? Okay.
When do we make money?
Good question.
Well,
Do you have any comment?
I'll answer you that. I was thinking about, since if we're wrapping up, if any final thoughts, I want to do a pitch for RISC-V, and perfectly for your question. One area, we talk about AI here, right? One of the other area, it's very hot right now is auto, right? The autonomous driving. For auto, one of the key requirement is for safety reason, you need redundancy. And for redundancy in the legacy, ISA, how do you do redundancy with ARM, with another ARM chip, right? And in RISC-V, you can do a very perfect redundancy. That redundancy will be even from different IP, not just different SoC. So your safety will be much more improved. That your redundant chip is from a different SoC vendor with a different IPs, and everything is different. So you have a perfect redundancy. So that you will sell more chips.
That is a good comment. So how about Frankwell? Do you have any comment?
Yes. From RVI already started to make money because the strong membership increasement. So, yeah, applause. RVI already started to make money. Okay, so we have a strong leader here. We believe with that, every other companies, when they pass through the taking off stage, they will start to make money.
I have a question. Why ARM can earn money, but RISC-V is more difficult than ARM? Do you have any comment?
I have a different observation. ARM is under very strong pressure from Masa-san, SoftBank. And SoftBank had 10 years very huge loss. So there's a big gap that SoftBank require ARM to fill up. It's been reported as 100 billion. That's why when ARM first time they tried to sold it to NVIDIA and not make it, and then they tried to IPO. With IPO, ARM's market cap is like 300 billion. That filled up 30% of what SoftBank requires. Now, the point is whether or not SoftBank keeps losing money, or now they return from that kind of a big loss. I don't have a further report, but again, with that, ARM looks like turning to a different kind of a mindset. They started to do a chip design. They tried very best effort to fill up their boss expectation. So they kind of dealing with customers in another way. They are not afraid to make customer angry, okay? people like Qualcomm. They sue them, right? So if you have a vendor, they sue you, and well, what do you think? Even they make money. So what? It's no big deal. I should prepare backup solution. Anyone dealing with ARM, you got to be careful. Maybe tomorrow you got sued. So you have to prepare alternative. That's my observation. And RISC-V is the good solution.
Okay, thank you. Other comments? Okay.
Yeah. So, sorry. So, Andes is a public company in Taiwan, so you can go there to check how we are doing. So I don't want to say too much here. But we just have a lot of customers using our product, either replace ARM or maybe they'll start the first project using Andes, quite successful. So I think we are quite happy. So as we help more customers to be successful, that's our mission. So I think Yuming, certainly we hope we can help you to make money soon.
Yeah, so I think I have a slightly different perspective. So I would say we've done a good job promoting RISC-V as an open standard. And I think what's missing is high-performance implementations. I think that's what a lot of people are looking for. And I think Tenstorrent and others that are working on these high-performance implementations, once we're able to ship those and actually get them in systems, that's when real change will take place, because people will be able to run software and say, oh, the performance is as good as ARM or x86 or even better, right? And then that's where the rate of innovation will sort of kick in and gain wider adoption. The other thing is people that are currently using ARM, for example, there's a bunch of IP that surrounds, system IP that surrounds ARM, which today is not widely available across all the RISC-V ecosystem. There's not potentially open versions of all of them, right? So you have, every company has to develop their own version or find some other solution, right? So I would say those are some of the key challenges. Yep.
Okay, thank you. So the conclusion is...
I think I want to add one thing. I think the comparison for ARM versus RISC-V might be slightly different, because RISC-V is an ISA, right? ARM is one of those earlier RISC, right? So if you compare RISC-V with all the RISC company, ARM needs to make a lot more money to make up all those bankrupt RISC companies now, right? The SGIs, the DEX, all those companies, they are no longer exist. So I think ARM needs to make a lot more money to catch up with RISC-V.
Okay, yeah, so the conclusion is sooner or later we will make money. Probably stronger than ARM, right? Okay, thank you for all your joins today's activity.
Thank you so much, Dr. Jeffrey. Now we would like to have the opportunity to have a quick photo. You may please stand up. Perfect. 3, 2, 1. Okay, another one, we have V as RISC-V. All right, thank you very much. Now, gentlemen, you may go please back to your seat. All right, it was a very engaging discussion, yeah? Now we already see a box, our magic box. Now I will check first the energy, okay? Okay, let's see. Good afternoon, everyone. Wow, I think everyone is either sleepy or wanting to go early, right? So let me check one more time. Good afternoon, everyone. You still have energy? Yes. Do you want to win another prize? Yeah, half yes. All right, so ladies and gentlemen, it's going to be our afternoon session. Thank you very much. Before we officially wrap up our RISC-V Taipei Day, we have the final highlight, which is the lucky draw. We would like to express our sincere gratitude to Syntronics for their generous sponsorship. Now I would like to please welcome Mr. Frankwell again to have another draw. Now, as you can see, we have the Marshall Willen Bluetooth speaker. Now, Mr. Frankwell, are you ready?
Yes.
Are you hungry?
No.
No, perfect. Okay, just to check, yeah, the concentration. All right, so in 3, 2, 1, you may go ahead and put another card. Hopefully the person is here. If not, we will have another round, okay? All right, you may go ahead. Okay, you can check it so that it's not Endes Technology anymore. Okay, we have not Endes Technology. Okay, can you please call the name and from which company?
It's from QNAP, Mr. Tim Lin.
Tim Lin from Q. Oh, we have. Let's have applause for our first winner. Okay. Now we would like to invite you. Okay. To have a picture together. Yeah, please look happy. Yes. Thank you very much. Very lucky guy. Okay, now we have another one. Don't worry, don't worry. Our sponsor today is very generous. Now the next, what we have is another Apple iPad Air. Let's have applause for our sponsor, Syntronics. Okay, are you guys ready? Yeah. Yes? Yes? Who wants to have another iPad? No one wants? No one wants? Okay, well, I do. Joking. All right, Mr. Frankwell, you may go ahead and pick one card. Oh, okay. No name? Okay.
The same with this morning, NYCU Meng Yuzhen.
Oh. Wow, congratulations. Wow. So previously we have another student. I want to check. Are you a student?
Yes.
Yes, you are a very lucky student today.
The same person for same prize, the same lucky draw, same university, same one. She's the one we had the lucky draw this morning. She was not here. Yeah, she was told but 2 times.
So this is actually your day. Wow. Okay, look here. Wow. Okay, well, we cannot beat this. Maybe God really wants her to win something. Oh. 1, 2, 3. Okay, thank you so much. Oh, wait a minute. I will ask you. How do you feel winning 2 times today?
My pleasure very good. Okay.
Do you do a lot of good deeds?
I know make money.
Oh, okay. So I think you should work for him because he was asking how to make money.
We are good friends.
Okay, all right. So maybe I also want to be your friend. Okay. Thank you very much. Thank you. Thank you, Mr. Frankwell. You may go ahead, go back to your seat. Oh, wow. Actually, that is very impressive. We have 2 names at the different lucky draw, but it's exactly the same person. So, if you're lucky, you're just lucky, guys. Now, thank you so much on behalf of the organizer. Thank you for the speakers, the panelists, and also sponsors, especially to every one of you that joining us today. There are some from Spain, from US, right? Is there anyone not from Taiwan? I heard some people are from Japan, right? There are some people from Japan also. Wow, thank you so much. Your enthusiasm and also support are the driving force for our growth in the RISC-V ecosystem, not just in Taiwan, but also globally. So we really hope today's session will inspire new ideas and also connections and also opportunities. And if you would like to explore more about RISC-V technology, don't forget to visit us at the 4th floor, L0425. Also, if you want to stay connected and latest update, feel free to scan the QR code. So I will give you some time to do a QR code. Oh, I cannot because of the chair. No problem. So thank you once again. My name is Laras. We look forward to seeing you at next year RISC-V Taipei Day. Thank you very much and good afternoon.